Where are you, Dylan? Where's Joshua? So the temperature is not what we know again. I had to get somebody to unlock the room today. I guess in the summer they just kind of forget about classes. The staff does. So I have to talk to somebody and have them unlock the place for us. Either that or give me a pass key. That would be better. Okay, so before we get back into chapter 10, I want to talk about modifications I've made to the grading schedule. So look that up. So, and the syllabus has been, the upgrade to the syllabus has been posted in Brightspace. I just didn't make hard copies. So since we're not having a comprehensive final, what we did have, I did have as a final percentage has been blended into the chapter exams. So we've got 7 of them, if I counted right. Yeah, 7. So that's 10% each on your total average. And then I'll come back to this in a second. These are the same, 20% homework, 10% participation. The crossword puzzles, I've decided to make those a 10% component extra credit. So 70 plus 20 plus 10 is 100%. And this average of your crosswords will give you actually an extra exam grade, all of the crosswords together. And I'm leaning toward doing your average without the crossword values in there, and then incorporating the crossword puzzle values in and see which one gives you a higher grade. And if the crosswords bring your grade down, I'll throw them out. Okay. Any questions from the peanut gallery too? Nope. Okay. Let's get back into chapter 10. And let's see if this works. Nope. It's not working. Let me pull out my dongle and stick it back in. That's what it needs. It's not working. Maybe it doesn't like that slot. Put it in a different slot. There it goes. Yeah. Come on. Yeah. All right. I don't have time to mess with that. Let's just do it the old-fashioned way. So let me get back down to, let's see, go past this one, go past that one and that one and that one, and past this one. That was where we were last. Now we're going to pick it up here with closest packing model. We talked about unit cells to begin with, and then the video that I showed introduced a little bit of the closest packing. Now we're going to take a look at that pretty much exclusively until the end of that discussion, and then we'll try to pull them both together as best we can. Okay, so what do we mean by closest packing? It's really very simple. It's like looking at a jar of marbles, right? If you just pour the marbles in, then they might settle to a certain place. But if you shake them, you might see them settle some more. That just means that the marbles are finding spaces to move into and minimize unused space. So we're packing them as close as possible. Now that's a physical model, that the jar of marbles. In the chemical, when we add the chemistry to it, sometimes the lowest energy may not be what we consider the best physical packing. In other words, I think our, let's see, what was it? Was it this one, polonium? Polonium was and the unit cell model was the simple cube. Right? So you had polonium atoms here, and that left a lot of empty space. But so why would polonium do that? It would do that because this is the least energy, the lowest energy level for polonium packing. Right? There's no advantage to assuming a different three-dimensional arrangement. So always keep that in mind when you're trying to determine which is the preferred outcome for any process, which one has the lowest energy. And that's not the lowest energy overall, it's the lowest localized energy. And nitroglycerin is a perfect example. Right? Nitroglycerin has a lot of energy packed into that molecule. So you would think that when you react sulfuric acid and glycerin and nitric acid, you would get something of much lower energy state. There it is. But instead, you get something that's packed with a lot of energy. The nitroglycerin molecule, and all you have to do is just look at it cross-eyed and it'll blow. So it's an unstable situation, but it's a localized minimum. So when I say the lowest energy state is the ideal, it's the lowest localized energy state. Okay. Just wanted to qualify that. Okay, so now when we're packing these atoms together, think of them as uniform hard spheres. And we have several options that are available to us. How can they pack together? And like I've always said, nature just does what it does, and we're trying to explain why it is this way. And there are several options that we have for packing these spheres together. I wish I could get this thing to work. Let me try it again. Maybe this needs to be moved out here, and this one needs to be moved there. Oh, well. Next slide. Oh, next slide is a video. Okay, this video, I think takes quite a few minutes. Yeah, it's about 12 and a half minutes, right? And fair warning, the narrator here is a female from India. So start tuning your ear to the Indian accent. Okay.
The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A-type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice and its unit cell is primitive cubic unit cell. Dimensional close packing from two-dimensional hexagonal closed pack layers. The three-dimensional hexagonal closed pack structure can be obtained by placing two-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a two-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are two types of voids: tetrahedron voids denoted by T, octahedron voids denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the four surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the six surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A type and the second layer as B type, then the third layer will also be A type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres. 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
Now, did that help or did that confuse? I hope it helped. It was slow. Actually, if I'd been there, I'd want a cattle prod and a poker say, moving along, moving along. Okay. I'll make one point that struck me is the ABAB and the, let's see, this way, the ABCA, they both have coordination numbers of 12. Okay. And then once you got to this one, did you notice that hexagonal close packing or face-centered cubic? So this one will give rise to the unit cell that has face-centered cubic structure for the unit cell. So there's one relationship, correlation between the close packing model and the unit cell model. That's one point of intersection for the two. Okay. So let's see. This slide talks about the closest packing model of AB packing, where the second layer is exactly like the first, but it's shifted. So it's in a different three-dimensional position from A. But then when you come back and lay another layer of those two-dimensional arrangements on top, it lines up with the first layer. So that's your ABAB. And this is also hexagonal closest packing. Yeah, I call that one hexagonal. That's well, I've got it in my notes. What do we mean by hexagonal? 6 sides, right? So when we were showing the video and they were only talking about 2 dimensions, then you find that the coordination number for one, when they're offset enough to fit into the depressions of the first row, and you keep packing them like that, then the coordination number of one of those spheres is 6. That gives you the hexagon. I think that's where this terminology comes from. The ABCA is that one where the B doesn't line up with A and C doesn't line up with either A or B until you get back to A again. And the way you accomplished the AB was the B's fit in the tetrahedral voids. Of A. But when you get to the ABCA, each one of the new layers fits in the octahedral voids. That's the fundamental difference between the two. And here we get, there we go. Now we get the face-centered cubic unit cell from that type of closest packing model. All right. So now we've got hexagonal closest packing. I wonder if both of them are not. Both of these are not hexagonal closest packing. And the face-centered cube is a consequence. I'm not going to go into a lot of depth on this, so I wouldn't be too worried about that one. If the book gives you a better explanation, then by all means, incorporate that into your brain cells. Not your brain, your synapses, right? Brain cells stand alone. Memories are caused by synapses and pathways. So here we have the relationship between ABCA and the unit cell, which would be the face-centered cubic. Let me go back. This is ABA, and it also shows a face-centered cubic. So both of them are hexagonal closest packing. Only one is an ABA type, and the second one is an ABC type, and they're both face-centered cubic. There wasn't too much emphasis placed on the type of packing where you have the AAAA. That would definitely give you a, well, the video actually made mention of that, would give you a, they call it a primitive cubic unit cell. We just call it the cubic, simple cubic unit cell. Would be, and that one would be the one that we saw earlier for polonium. And there's a lot of wasted space in there. Knowing how much space changes from one model to the next can also help you determine or actually calculate densities. If you know if you have a pure substance, pure metal, for instance, and you know its packing model, then you can calculate its density because you know how much space is occupied. And we're going to talk about that in a minute also. This coordination number for both of these, ABA and ABCA, the coordination number is 12. And that just means that if you take one individual sphere, you can find it in contact with 12 other neighbors. And this is in the three-dimensional mode. If we go to one dimension, if we look at that A layer, then the coordination number on 2 dimensions is 6. Okay, we went over this one in the last meeting. How many atoms in our model, or how many spheres can be attributed to the unit cell? Right, and we said that simple cubic was one cell, one sphere per cell. Because if you take the cubic model, and I think the first video we saw was I think that's why I put it in there, was it had the razor blades come and slicing between the So if you do like this, and you look at just one of these spheres, well, okay, if you slice this off, so that unit cell is removed, then what do you have left? You got a half a sphere left at this point. But then if you come in and slice it this way and take that off, you've taken a half of a half, which is a quarter. So now you only have a quarter of a sphere left. But if you take it, slice it here, now you've only got an eighth of a sphere left. So if you slice it 3 dimensions, one in sequence, then you whittle it down to this is only 1/8 of a sphere belonging to that cube, and there are 8 of them, so you have 1. Now you know me already. Okay, there you go. All right. So in this case, though, we have how many spheres per unit cell? Well, you've got the corners, right? That's 1. And then you've got how many faces? 1, 2, 3, 4, 5, 6. 6 faces and half a sphere per face would be 3 more. So this should be 4. There you go. So you have 4 spheres, or if we're actually talking about atoms, you have this sphere owns only 4 atoms. Simple cubic, let's see, we got 1 metal atom for the cubic, and the face centered is 4. We didn't do the body centered. How many, remember how many for the body centered? Well, the corners have 1, right? But there's 1 hole in the center that belongs to that cell and none other. So that means 2. Right, so it's 1, 2, and 4. If you step your way up from simple to face centered, simple to body centered to face centered. Okay, so suppose we have a metal that crystallizes in a simple cubic structure. What's the relationship between the radius of the atom? We talked about that in the earlier chapters, atomic radii, and we know the trend on the periodic table. Right, they get the atomic radii decreases as you go from left to right, right? And it decreases also as you go from low bottom to top. So from lower left to upper right, you decrease the radius. Well, we're going to use that information in this scenario to relate the radius of the sphere, or the radius of the atom, to the length, the edge length on our cube. So this edge length here, let's see, I want to use the right terminology. It doesn't have a symbol for it, so let's just call it A. So that's the edge length on that cube, and now we know the volume of the cube is just R cubed. Or A cubed, excuse me, A cubed. The volume would be A cubed. Okay, so how does that relate to the radius of atoms? It depends on the cubic cell, on the unit cell. If it's a simple cube, then all of these are touching one another, right? So we know that if this is like that, and they're touching, then we know that this is the radius here, and this is the radius here. And if they're the same atom, then that's an R, and that's an R, and A equals 2 times R. Okay, the edge length is 2 times R. This is the simplest one to rationalize or use simple geometry. And if we know that, then the radius of the atom tells us the edge length, and that relates to the volume. So that we relate the volume of the unit cell to the radius of the atom. And obviously, if the atom gets bigger and it's in this type of unit cell, then the volume will increase. The face-centered cube is a little different. Then I had a handout, but I said, well, I've got handouts, and they're in Brightspace if you want to look at them, explaining how these formulas were derived. The edge length of a face-centered cubic. So if we put a face-centered cubic, we put one here, here, and here, and back there, and over here, and down here, then these no longer touch. Right? These atoms at the corners no longer touch. So how do we determine the length there? Well, there's some geometry involved, and it turns out that this edge length is the radius, this A, equals the radius of the atom times the square root of 8. Okay. And that handout will show you if you're curious and you want to know how it's derived. And it doesn't use calculus. It uses simple geometry and trigonometry. And the one we have left is body-centered cube, right? Are we going to do the body-centered cube? Yes. So if you have a body-centered cube, now you don't have any on the face. Let me draw another cube here. Now you still have these at the corner, and they don't touch, right? Because you've got this one in the middle that keeps them apart, but you still have a radius here, and you still have an edge length, A. So how are they related? Well, as it turns out, they're related. A for this one is equal to, and I can't remember it, the radius of the atom times 4 over the square root of 3. Okay. And those formulas are in useful information. Okay. If you come take, like always, if you come take a paper test, it'll be on the back pages. And if you take the test in Brightspace, then in that folder where you find the connection to do the lockdown browser test, there's also a separate useful information document. So if you don't have it handy from the useful information, the review document, it's a duplicate of that. So if you have the review document, just tear the pages off the back and you can have that during the exam. And these formulas will be there. You just have to know how to use them. So. Okay. So for this example, we're going to calculate the density of silver with that information. And I've got an animation, and it's all the calculations are going to show up in that box. But I'm going to see if I can do it without the help. Let's test a mental acuity. Okay, so we're given silver. We know silver is the atom that's being packed in here. We know that it's cubic closest packed structure. Okay, so it's going to be like polonium. Silver is going to be a simple cubic. Okay. So it's simple cubic. It's a unit cell. All right. What else do we know? Oh, excuse me. No, it's not. It's not simple cubic. I need to read further, don't I? It's face-centered cubic, correct? Face-centered. Face-centered cubic. Okay. Now I know we're going to need volume. All right. So before it fades, let's recall what the relationship is. Not that. What's the relationship between that edge and the radius? Wasn't it square root of 8 for a face-centered cubic? Square root of 8. Oh, I can look back here. Okay, hard copy. Yeah, there we go. Face-centered cubic. So we know that's the edge of our cube. So our cube is going to be like this. And it's going to have silver atoms at each corner. And this edge, A, is going to be related to the radius of that silver atom of that formula. Okay, if we're going to calculate the density, we need to know, well, actually, calculate the density. cell edge is 409. Okay, so we don't need to know that. Right? Because it already tells us that this is 409 picometers on an edge. Okay, so how do we calculate the density? Think way back to the beginning of first semester. Density, let's see. I do that. I start right here and then I have to write over here, and then I got to go back over here. And that's a mess. So density equals mass per unit volume, right? So we do need to know the volume of this unit cell. And that would be, let's do the volume over on this side. Volume equals 409 picometers cubed. Right? Okay, so what's a picometer? A picometer is 10 to the minus 12 meters. Right? So we could say, but we want the density in what terms? Usually solids, the density of solids is in units of grams per cubic centimeter. Right? So, I mean, before I trip over something. There we go. Okay, so we need to convert this to cubic centimeters. We could go ahead and calculate it that way. Or we could make some more room, since we're not going to need that. And we could go ahead and convert picometers. This is in the numerator. This would be in the denominator. And we know the relationship of picometers to meters. So we can put that one in here, right? It takes 10 to the 12 picometers to make a meter, right? Okay, but we need to cube it. So now how about meters? Well, meters we're going to cancel, and centimeters would be here. All right, so we have 10 squared centimeters per meter, and that needs to be cubed. So by cubing this one and this one, that cancels that one. And by cubing this one and this one, that cancels that one. And leaves us with centimeters. So let's crunch some numbers and get our volume. Okay, so 409 cubed. Here. I'll just go ahead and write it here. In case I make a mistake, then I can go back and check it. 4 times 10 to the 7th cubic picometers. And this one is, let's see, we've already canceled those, so we can move this one over here, right? When we cube a square, what do we have? 10 to the 6th power, right? 2 times 3. 10 to the 6th cubic centimeters here. And then over here, we have 12 times 3 is 36, right? Yeah, 36. And that's cubic picometers. And the only reason I'm writing picometers in here is because I wrote it over here, so we can still cancel it. Okay, did I do anything wrong? Cubed, 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 cubed. There we go. So now all I need to do is to resolve this one. So what's that one? Well, this one goes out, this one becomes 30, right? 10 to the 30. So I just need to divide. So 10 to the 30 is in the denominator, 10 to the 7th is in the numerator. So what would the exponent be now? 6.84 times 10 to the -23. There you go. And this is cubic centimeters. So we have our volume. Now we need mass. Okay, this is the volume of the unit cell. Right? How many atoms of silver are in that unit cell? 1 atom, right? 1 atom of silver. All right. So how many atoms in a mole? Right, because we know the only way we're going to get to mass is through the molar relationship. So we got to get this into moles. 6.022 times 10 to the 23rd atoms per mole. All right, so that gets rid of atoms. Now we got moles. Now we can convert moles to grams. We just need the molar mass of silver, which is 107.87. There we go. So this is going to be our mass. Let's see, 107.87 divided by that huge number. There we go. So this says we have 1.07, no. Mistake, I stuck an extra O in there. 1.79 times 10 to the minus 22 grams. Now we can calculate our density. We just need mass. 2 divided by volume, which is 6.84 times 10 to the minus 23 centimeters. And let's see. I think it'd be simpler for me just to punch that one back in. 6.84 exponent sign and then divide. So I get 2.62 grams per cubic centimeter. Now let's see if I made any mistakes. Yeah, I did make a mistake somewhere. All right, let's see where it is. This is right.
If you did 4 atoms.
Of course. They center cubic. 4 times. Times 4. And that should be times 4, which is 10.5. Okay, that's what comes from not paying attention to the instructions. I wish I could say I planned it that way. Okay, when you compare that calculated value to the experimentally determined, it's almost exactly the same. In fact, the 3 significant figures, it is the same. There we go. All right. So I'm going to let your brain rest a little bit with 3-dimensional gymnastics and talk about something a little bit different. The elements that tend to fit those models the best, either the closest packing or the unit cell, are metals. So we're going to use that as our segue to discussion of bonding in metals. The earliest concept for bonding in metals was called the electron C model, in which you just have, it's kind of like, it's analogous to the plum pudding model for the structure of an atom. Right? You have the positively charged nucleus of the metal, and you have this electrons in around it, and they're packed in there in whatever arrangement that we determine. And those electrons are just like, they're like fish. They're just flying everywhere. That's the electron C model. The C, of course, would be the electrons, and the nuclei of the metals would be the whatever. But that was a starting point. It didn't explain very much, right? The model needs to explain physical and chemical characteristics. And what are the characteristics of metals? Right? Well, the physical characteristics, they're shiny, they're malleable. In other words, the atoms can move past each other with a little push. They're good conductors of electricity and heat. So something in there has to move, right? Heat is an expression of kinetic energy. It's motion. So when you take a chunk of metal and you put a blowtorch on this side, sooner or later, you're going to feel it on that side. Assuming there's a barrier in between, you don't feel the torch, then you'll feel it on the other side of the metal because it conducts the heat very well. So how does the heat get from here to here? Well, there has to be some kinetic energy, at least some vibrational energy that's imparted to the metal atoms, and they have to transfer it through. Right? Well, we could explain that simply by atom movement. But how do you explain conductivity? I mean, it's electrical conductance. Right? The atoms don't move, not the solid. And so the only thing that's mobile in these atoms is the electrons. So the electron seed model, I think, tried to approach it from that angle. You have these electrons floating out here, and they're free to move from atom to atom. And you just put a potential difference across that metal, and you can get those electrons to zip across because they're not held very strongly. The problem with that is it doesn't lend itself to any quantitative measurements or determinations at all. So the next best answer to that is the molecular orbital model or the band model. And that's where we're headed. This is what the electron C model would look like. And it's just a pretty picture. It doesn't tell you much. In this case, it's like all our study of molecular orbitals takes the mass of substance, whatever it may be, whether it's an individual molecular compound, or whether it's a chunk of metal. In this case, we're taking a chunk of metal, and that whole chunk of metal, all of the orbitals of the electrons in that chunk go into the model, and they produce this molecular orbital now structure for the entire mass. Right? Nobody owns their electrons and their orbitals anymore. They belong to the group. It's like it's the communist model for chemistry. So what we find is, if we only have two atoms of metal, then we get these two molecular orbitals that we see on the left-hand side, and there's a pretty good gap between them, an energy gap, right? You can think of those as bonding versus anti-bonding. Well, if you put four of them together, then they get closer together. So what that means is it's easier for the electrons to jump between orbitals. All they need is a little push. If you put 16 of them together, they get even closer. Well, if you put a whole mole of them together, it's virtually a continuous layers of molecular orbitals. And the gap between them is so small, all you need is like a voltage difference of, say, a microvolt, and you can get electrons to move because it doesn't need much push to go from one orbital to the next. And if we look at it in terms of, if we try to visualize this structure, the molecular orbital structure for atoms as they're layered in their closest packing model or their unit cells, which is most suitable for understanding the physical phenomenon, you find that there are at the very outermost layer of the molecular orbitals, which is shared by every atom. There's a layer out there that has been filled up, right, using our Aufbau principle, filled up lowest energy to highest energy, and then you have this molecular orbital layer that's out here that has no electrons in it. That's what that upper layer is. I wish my pointer worked. It won't work for there, but I can make it work here. Right here. Right, empty molecular orbital there. And it takes just a little bit of push to go from here to here. And what that means is, relative to one atom or the next, it can go from, if there's an electron here and it gets a little kick from there, it can go up, just make a little jump over to the next atom. And this can be, oh, it's moving now. Okay. You can just get a little kick over from the next one. So that's why metals are good conductors. It takes so little energy, either heat or electricity. Yeah. The electrons are doing the busy work, most of the busy work. Now, of course, if you heat it up, the atoms are going to vibrate, but they're also going to throw electrons, add energy to the electrons, and they can move into that empty molecular orbital and move over according to which way the voltage, the potential moves them. And we're going to talk about potential in detail in chapter 18. So I'll leave the definitions till then. Everybody knows what voltage is, right? Low voltage is a tingle and high voltage is a shock. Okay. So change gears again. We had, up to now, we discussed the pure metals, right? How they stack together and their, how we can account for their physical and chemical properties, primarily physical, with the molecular orbital model. But they're not very functional that way, with a few exceptions, right? We use gold-plated contacts in things like computers, right? Because they don't corrode, and it's a very good conductor. The only conductor that's better is silver. Silver is the best electrical and thermal conductor in the periodic table. So that's why if you've ever built, a computer at home, right? When you build desktop computers, you get the motherboard, and then you get the CPU that you have to buy separately and hope that you bought the right one, and it fits in the slot. Well, you want good contact, and you don't have to do anything about that. You just set it in there, and it's got notches to make sure they line up, and then you lock it down. But you want to be able to get rid of the heat, right? These CPUs are packed in there tighter and tighter and tighter with each generation, and they generate lots of heat. So you need to get rid of that heat. So you put a cooler on top of it, and that is smack on top of your CPU. But you want to be sure that there's good heat conduction from the CPU to the, actually, they usually have a big metal plate and then heat pipes filled with fluid. And that wicks away the heat and sends it up to either a fan or through a liquid circuit to an external fan. And the way you get that good contact is with this paste. And the paste is impregnated with silver, pure silver. And this tiny little tube costs like $5 because silver is, you know, a precious metal. But it's a very efficient conductor, and it's worth the expense. But to augment the physical and chemical properties of metals, we often combine them, or combine non-metals with metals also to make alloys. An alloy is just a homogeneous mixture of a metal and something else. Could be another metal, it could be a non-metal. The most common non-metal used in alloys is carbon. We put carbon and iron together and get steel. But these alloy atoms fit into the metal, I guess you could call it a solute. Have we defined our terms yet? We did talk about that last semester, didn't we? Solvents and solutes. Okay. So the solvent would be the major component metal, and then the alloy part would be the solute. And you can put it in there. Where does it go? Well, it has two options. If the solute of the alloy that goes in is too big, then the only place it can go is to knock one of the solvent metal atoms out and substitute for it. That's a substitutional alloy. And the one I like the most is copper and nickel. So copper is the solvent, and nickel is the solute, is the minor component. Okay, and if you do that in the right amount, you get brass, right? And there are various compositions, right? This is a mixture, right? So these atoms don't lose their identity when they go into the mixture. They can be separated by physical means. But you can get different grades of brass, right? Most ships still have fixtures, external fixtures are made out of brass because it doesn't corrode easily. Or your musical instrument would be made out of an alloy, copper and nickel. And sometimes over the years, they've discovered you add a little bit of something else and it improves some property. That's a substitutional alloy. So for every missing copper, you get stick a nickel in there. The other type is interstitial alloy. And remember, we talked about those voids, the tetrahedral voids and the octahedral voids. For the interstitial alloy, the atoms, the solute atoms are small enough, they can fit in those voids. So you still have all of the, I'm going to use steel as an example. You still have the iron atoms like that. And then maybe it's like this. I don't know for sure. Maybe it gives us a tetrahedral void. And you get a carbon atom, you get a carbon in here, stuck in those voids. What does that do? Well, pure iron is very malleable. You can scratch it with your fingernail. But when you put carbon in there, it locks the crystal structure, keeps it from moving. Right? So that's why steel is very hard. And there are various grades of steel too. And you can add other components in there to make a different type of steel. Like stainless steel, you add a lot of chromium. Originally, it was 35% chromium by mass. I'm sorry? Oh, yeah, sure. So we would substitute. We'd have an interstitial and a substitutional type of alloy in most modern steels. Okay, you just plug the chromium in here. Every third or fourth atom would be chromium. But you still have the carbon in there. Now, those are the two basic types of alloys. And there's a visual representation of them. Okay. So now we're going to shift a little bit again. And now instead of metals, we're going to look at allotropes of carbon. Didn't we mention allotropes early on? An allotrope is an element. An allotrope of the element has a particular structure, but it's still the element. And then another allotrope of the element is still the element, but it has a different structure. And this is a perfect example. Carbon, if we have a three-dimensional tetrahedral arrangement, covalently bonded carbon atoms all the way through the diamond, then I painted myself into a corner. I don't know how to finish that sentence. All of these carbon atoms are covalently bonded in a tetrahedral structure. Then you have diamond. And this only occurs at very high temperatures and very high pressures. That's why naturally occurring diamonds are formed very deep in the earth. And the only reason they're brought close enough to the surface for us to get them is through volcanic action. So you find, I think they call them kimberlite pipes. And if you can find one of those, then you know that you're onto something. And you can mine that particular geographic structure and there are going to be diamonds there more than likely. And South Africa is covered with
What is it called again?
kimberlite, kimberlite pipe. It's a pipe because it's shaped like a straight tube.
Could be somewhere near a volcano.
Yeah, it's volcanic action brings it to the surface. Yeah, and it doesn't have to look like our typical.
Is there volcanoes in South Africa?
There were at one time. Yeah, we're talking about geologic
Yeah.
time. And volcanoes don't necessarily have to form a cone.
Yeah.
Right.
Yeah.
Some of them do.
Yeah, volcanoes in the sea.
Yep. Yeah. And you get the Hawaiian Islands are a different type called a shield volcano.
I wonder if there's diamonds there.
Not likely. No.
Was it not pressure?
I don't think the conditions are right. Right. Because the magma that's coming up for the Hawaiian Islands comes straight from the mantle. Right. It's not picking up anything on the way. Right? So there are volcanoes and then there are volcanoes. But anyway, this is one allotrope of carbon in that three-dimensional structure. And that also illustrates the point that the unit cell doesn't have to fall into that simple cube, body centered cube, or face centered cube. Those are just three of the most common examples. There are hundreds of other different types of three-dimensional structures, simple cube, cubic type, or they don't even have to be cubic. You can take the simple cube and you can do things to it. Like you can take it and hold one side steady and grab the top and go, and get a rhomboid. And you can see that in calcite. You ever seen a crystal of calcite? It's calcium chloride or calcium phosphoride. Calcium fluoride. If you have a chance to get your hands on one, they're transparent. But if you hold it over the written word, it'll split that into two, and you'll actually see two sentences. It says strange optical effect. Anyway, another way that carbon can arrange itself is in graphite. And in graphite, you have covalent bonds in this hexagonal shape, right there. And between the layers are intermolecular forces, right? So since carbon is nonpolar in this arrangement, those have to be London dispersion forces. So they're very, very weak. And that's one of the reasons that graphite is often used as a dry lubricant. Because when you put pressure on that graphite and slide, one layer goes this way and the other layer goes that way, and the forces between them are very weak. So they allow you to slide past with great ease. I used to keep a can of powdered graphite next to my motorcycle. And when I needed to lubricate the cables, it had this long tube, and I just put the tube at the top of the cable and just it went down in there. The nice thing about it is it's not moist, so it doesn't collect dust or dirt. And that was particularly useful for my dirt bike.
I look like to do that.
Kawasaki 175. Okay. My brother had a Yamaha 250, but we tried to cross a creek one time. We knew that there was a structure, a concrete structure that was about this wide. Couldn't see it from the surface, but it was about this far below the water.
Yeah.
And we were going to stay right on that. Well, he got off to one side and shoot. So I helped him drag his bike out of the water, and we took the spark plugs out, tipped it up, and got the water out of the cylinder and put the plugs back in and cranked it up and went on our way. Anyway, the difference between these two in terms of their molecular orbital structure is, and this references the conductivity of the two. Diamond is both an electrical and a thermal insulator. It will not conduct very efficiently electricity or heat. And gemologists use that to verify whether or not if they've got to mount something in a ring setting, and the customer is claiming it's a diamond. All they have to do is take this device, touch the diamond with it, and it'll measure the thermal conductivity. And if thermal conductivity is too high, they got a fake diamond. So this is a molecular orbital explanation for that difference. The molecular orbital distance between the highest filled molecular orbital and the next available empty molecular orbital in a diamond is the gap is very big. So the electrons have you have to put a lot of energy into them to get them to move from one to the next. Whereas for typical metals, they're very close together. And for graphite, they're even closer. Not closer than the metal, they're closer than the diamond. So graphite is a better conductor than diamond is. Did I tell you the story about my wife's blue diamond? No. A friend of hers wanted to send her a tanzanite. It's another type of compound in a gem form, and it's a beautiful blue color. And it's named after Tanzania, where they're found in Africa. And so her friend said, all you have to do is pay for shipping. So I said, sure, right? They're not that expensive, so I don't feel like I'm robbing you or anything. So we paid for the shipping, and the gem was sent, and we took it with us to the mall, to K's, I think it was, and said, look at this beautiful tanzanite, isn't that pretty? You think we can have that mounted in a setting? So we were looking at settings. He said, the salesman said, that looks like a diamond to me. Says, no, not for what we paid for it, right? Yeah. So I said, wait a minute, let me get my device. So he brought out the device, put that on there, and says, whoa, that is a diamond. You got yourself a blue diamond. It's pretty good size. It's bigger than her wedding diamond.
Worth a lot then.
Yeah. So he said, okay, we need for you to send this to your gemologist and have it appraised, give us an official appraisal.
Yeah.
So we can put it on our home contract with State Farm. So they did, and we did that. And then we found a setting and put it in the setting. Well, we felt bad, so we told our friend what happened, and the friend said, my mistake, keep it.
That's crazy.
So her friend is kind of rich.
Yeah.
Okay, so here's another arrangement. This is an explanation of graphite, right? On the molecular, actually, remember when we were talking about benzene, right? You could draw the benzene molecule like this, with your carbons here. And then each one had a hydrogen. And if we draw it, right, with our my mind's gone blank. We draw the Lewis structure, we get a double here and a single here, but we know all these bonds are equal, right? So they're not really double singles, they're a hybrid, right? So they're all alike. And the explanation for the stability of benzene is this delocalization of electron density in those pi orbitals. So you have pi orbitals here, and they overlap. And they overlap all the way around the molecule, and they stabilize it. Well, same thing happens in graphite with these carbons. They don't have the hydrogens attached to them, because instead of the hydrogen, they're attached to another ring structure here, and there's another ring structure there, like that. So the hydrogens are missing, and it's just the carbons in this hexagonal structure. And they're stabilized by this delocalization of electron density in these pi systems. Okay. So that stabilizes the plate, but it doesn't leave any orbitals for overlap with neighboring plates. So that's why the only thing that attaches those plates to one another, attracts them, is the London dispersion forces, the very weak forces. Now, another type of solid is called a ceramic. Now, everybody has an idea of what ceramic is, just as a practical matter, right? You know, you can buy little ceramic figurines, or you get stoneware for people with my income, and you get fine china for people with higher income. But they're ceramic materials, and they're composed of non-metallic materials. And, very often, not always, but very often they have silicon in them, is one of the base elements. But when you put these ceramics, when you put the materials together and then you fire them, you change their molecular structure, right? The way that the atoms and the molecules are arranged, and that structure changes. The fancy word for it is a pozzolanic reaction. Now, after I say that, ceramic and pozzolanic and many of the terms used in reference to ceramics are operationally defined. In other words, they're what we say they are. Okay, so that they don't always have a direct link with the descriptive term and some atomic level fundamental theory. Right? We just define ceramics, and ceramics have been around for millennia. Right? We've only just, with modern science, tried to explain why they are the way they are. Well, they're usually composed initially of clays, right? And fine china would be made by a certain type of clay that's not very common. It's only found in certain parts of the world. And most of them are at the very base level are some type of silicate. Right? Sand is essentially silicon dioxide. Right? And you use it to make glass if you add some other things to it. But if you put these clays together, if you wet them and mold them into a certain shape and then put them in a fire, like 1200 degrees Celsius, then their structure changes. We do the same thing with bricks, right? If you have adobe structure, right, they're okay if you live in an arid region, because all you need is a little hay, you need some water and clay, dirt, and you just pack them into these big squares, and they pull the square off and go to the next one and let them sun dry. Okay? And then you build your house out of them. You get a big rainstorm come along and it washes your house away. Right? So if you want something more durable, then you stick those big bricks of adobe in the fire and change their structure so that they're resistant to external weathering. Let's see. Yeah, there we go. I didn't skip one yet. No. Okay. So another type of solid that can be formed is particularly useful for the computer industry, the electronics industry, called semiconductors. Right? We learned about insulators and conductors. And we talked about why each is the way it is with that molecular orbital model. Right? The conductors have very close spacing of their MOs. And insulators have wide spacing of their molecular orbitals. And I'm talking about those upper layer molecular orbitals. The semiconductors are somewhere in between. Right? So they're not quite insulators, and they're not quite conductors. But the nice thing about them is, if you put them one type in close proximity to another one, and the way they do it, of course, is they build them up on a silicon wafer. Then you can create switches. You can turn the switch on and off, so it'll conduct electricity, and then you turn it off with another. You have a controlling switch, and you can make that particular cell either a conductor or an insulator, and you have control over the movement of signals. And the way you do that is with two types of semiconductors, the N type or the P type. And if we use silicon as our base, right, pure silicon, and if you've ever seen, you can look these up on the internet. If you've ever seen a pure silicon ingot, they make them, and they're like 10 feet long. They're about that big around, and they grow them out of pure silicon. And it takes a while, but once they do that, then they shave them down and they slice them into layers and make these silicon plates. And upon those plates, they use photoresists and masks to imprint the circuitry on that disc. And then they dope the disc with a series of procedures. They dope the disc silicon with either those elements out to the right of silicon or to the left of silicon. So silicon has 4 valence electrons. It's a carbon family, so it's 4 valence electrons. If you dope it with something that has 5 valence electrons, then you get an N type, which stands for negative. You get an extra electron in that structure. And if you dope it with something that has fewer, you get a P type, or a positive type semiconductor. So if you dope silicon with, say, gallium or indium, then you would get a P type. If you dope it with phosphorus, or I guess you could use nitrogen or arsenic, is a good choice, then you get an N type. And I think the next slide. Okay, this approaches the N type versus P type in terms of their molecular orbitals. So if it's an N type, you've got this one extra valence electron sitting up there real close to the conduction band, the empty molecular orbital. So it can move, right? If you have a P type, then you're deficient of one electron or more, one or more electrons in the highest filled molecular orbital. And for convenience, it's easy to visualize the electrons up here being mobile in the N type. But what accounts for mobility in the P type? Well, these holes, they call them holes. They're not real insofar as they're things that move. The electrons move, and when an electron moves from one position into a vacant hole, it leaves behind a hole. So when the electron moves to the right, that hole moves to the left. So that's the way electronic engineers think of these things. The holes move, right? Well, we know they don't. But
The electron stack before then.
yeah, right. Right. Yep. So in that respect, they can conduct electricity. They can conduct a current. They can move a current based upon movement of electrons or movement of holes. And of course, if the hole moves, the current's moving the other direction. Right? So they can oppose one another. Now, the theory behind the semiconductors and how you put them together that's a little too much for this. So we're going to stop here. That's the way you make N type and P type semiconductors. Oh, there's an example. These boron. Okay, that's right. Boron is to the left of silicon, so it's deficient in that bottom one, right? The boron here. is represented by a hole. It's missing an electron. Whereas aluminum has arsenic, excuse me, arsenic has an extra electron. Okay. Now, what type of solids can we have? Well, ionic solids, in addition to the ones we've already studied, ionic solids, we characterize them as being very stable solids, and they have very high melting points, which accounts for their stability. And the cations and anions are locked into a crystal lattice. They do not move. That's why a solid chunk of sodium chloride, for instance, is an insulator, right? You can put 2 electrodes on either side of that thing and jack the voltage up to like thousands of volts, and it won't conduct electricity. The only time it'll conduct electricity is when you get enough voltage to heat it and melt it. Once it melts, then those ions are free to move, right? But as long as it's a solid, it will not conduct. And they're arranged. An explanation for what's responsible for this high melting point. Well, it's all due to electrostatics. Right? The melting point can be correlated with the strength of electrostatic attraction between the cations and anions. And that's dependent on 2 factors. Just like any 2 bodies that are negative and positive, they will attract one another. The closer they are together, the stronger the attraction. And the higher the charge difference between the 2, the higher attraction. So that's what we look at. Sodium and chlorine are single positive negative charge. Right? So there's a level of charge there that attracts them. Whereas magnesium and oxygen in that second one is a higher charge. So that factor in itself would account for a stronger attraction between magnesium and oxygen than for sodium and chlorine, and the melting point should be higher for magnesium oxide. But there's another factor, the size of the ions. Sodium is a small ion, but not really small, not too small. And chlorine is a big anion. So that puts their overall charges further apart, because you can only get so close and then you have to stop. So the overall attraction there is limited by how close the nuclei are together. Whereas magnesium and oxygen is an anion, but it's not much bigger than sodium. And magnesium is even smaller than sodium because it's to the right of sodium. It has more protons, so it's on the atomic level, it's going to be shrunk. But now it's losing 2 electrons. So it's shrunk even further. So magnesium is a lot smaller, oxygen smaller than chlorine, and you can get them closer together. So the combination of charge difference and distance between the nuclei gives you a stronger attraction between magnesium and oxygen than sodium does to chlorine. And that accounts for the difference in melting point. Right? It's not quoted here, but the melting point for magnesium oxide, I'd be willing to bet, is much higher than sodium chloride. And it's purely electrostatics. And we could use Faraday's equation. No, it's not Faraday's. Escapes me. I'll add it to the video as a caption. The equation that determines the force of attraction between 2 oppositely charged particles is based upon this size of the charge and the distance between them. Okay. Now we're going to go back to this 3-dimensional structure, the closest packing model, in reference to ionic solids. So previously we discussed this arrangement of spheres as if the spheres were not charged. Right? They were just all uniform, same size spheres, and they came in here and packed in a certain way. But now that we've got opposite charges and we've got different sizes, right? The cation typically is going to be much smaller than the anion. that it's associated with. Very rarely would it be the opposite way around. So the question then becomes, where if the chloride, if the anion is the bigger one, it's probably the one that's going to create the voids as it stacks in there. So is the cation small enough to fit in the voids? Or is the cation so big that it needs to occupy one of those other positions that where you would find the anion? That's the question in my mind. Where does the cation go? Well, if we're only on 2 dimensions, right? We've got these 3 spheres together, we've got a trigonal hole, right? But that's not reality, right? The world's not 2-dimensional. That's just a stepping stone to talking about the 3-dimensional structure. All right, so the comment here is that in a binary ionic crystal, binary would be what? Sodium and chlorine, right? They have the same charges. You only need one of each. Or magnesium and oxygen, they have a +2 and a -2, so it's just 1 to 1. So when in a 1 to 1 ratio, the holes are usually too small for the cation. So the cation does not occupy these holes. It has to fit into one of those positions that's not a void. So if we have this 3-dimensional structure where we drop a sphere into this trigonal hole, this void, and make a tetrahedral void, the example here is zinc sulfide, where zinc is the cation and it's small enough to fit in the hole. Right, so those blue spheres would be the sulfides, and the zinc would fit in that tetrahedral void. Oops, too far. So if we have an octahedral hole, let's see, where do we have a tetrahedral hole? Well, that would happen. That could happen with ABAs, right, where the second layer fit into the tetrahedral hole, or ABCA, where it actually fit into the octahedral hole. So this could be useful for any one of those. The octahedral hole is formed between these 2 arrangements of 3 spheres. And if you look at the drawing there, where you have these lines drawn, excuse me. There it is. These lines drawn, you'll find that you have 8 sides there. That makes an octahedron. Get that out of the way. So what are we going to do with it? Well, in order to ascertain whether or not the cation will fit in the hole, we need to know something about the size of the cation and the size of the void. So I'm not sure why the slide puts this trigonal in there, because the trigonal void is 2-dimensional, tetrahedral, octahedral, 3-dimensional. So that doesn't make any sense to me. I probably ought to modify that slide, at least make the comment. But the octahedral void is larger than the tetrahedral. So the octahedral void should be able to accommodate larger cations. All right, this is straight out of your book. All right, so I'm not going to spend a lot of time on this one. This just arranges everything that we've talked about and all the solids in terms of whether they are atomic solids, molecular solids, or ionic solids. And then the atomics are broken down into whether they're network solids like diamond, whether they're metallic solids like we studied early on, or they're this slide looks familiar. Did we see this one earlier? Maybe I'm thinking of another course. It happens. And the third type are the noble gases. And you can form solids with noble gases, except for helium. I don't think we can't get helium cold enough to make a solid. Right? You can make a liquid helium and it's down around 4K. Molecular solids are formed from either, they can form from polar molecules and give you dipole-dipole interactions. They can be non-polar molecules, and in which case the only thing holding them together is London dispersion forces. They're generally very soft, low melting points. Ionic solids are generally hard by contrast with high melting points, and they're not good conductors until you melt or put them in solution. Right? You got to get those ions mobile before they're good conductors. Okay, so now let's talk about this chapter's, excuse me, liquids and solids. So now we're going to talk about liquids. Let's see. Does anybody need a break? Are you all good? Okay. As long as I got my drink, I'm good. So let's suppose we put a liquid into a closed container. All right. If we put that liquid in an open container and just left it out, eventually it would all evaporate. Right. But if we put it in a closed container, what happens is initially, I'm just going to draw something simpler like this. If we put that liquid in an open container or a closed container, let's close it because I'll start off closed. Let's say we close it like that. Then you got molecules, atoms, whatever the case may be in this liquid, and they're leaving the surface. Why? Because the temperature is an expression of the average kinetic energy of the molecules. They're not uniformly distributed kinetic energy. In other words, the kinetic energy of the atoms in here on, let's say, numbers of atoms, and this is the temperature. Some of them will be lower temperature, most of them will be here, and some of them will be here. Right? Most of them will be at this temperature. Actually, what we could say kinetic energy. Let's do it that way. So these would have low kinetic energy. These would have high kinetic energy relative to most of their neighbors. Okay. So these guys out here have enough kinetic energy that they can leave the surface and become vapor. So when that happens, what happens to the average kinetic energy of the liquid? It goes down because you're losing some of that. So now if you average these all together, you get a temperature that's lower, right? That's why when you drop alcohol is a better example, alcohol or ether or something like that on your skin, it feels cold, right? Because these high energy ones are leaving, and the average kinetic energy drops the temperature, and you feel that temperature difference on your skin. But this is what happens initially when we first cap it. Okay, now you got some of these out here in the vapor phase. Well, they have an average distribution too of kinetic energy. And some of them have low enough kinetic energy that they're going to return to the liquid, right? And there comes a point where you get enough of these in the vapor phase that the rate of their return is equal to the rate of their evaporation. So the condensation rate equals the evaporation rate. At that point, you have equilibrium. And this is a physical equilibrium. Right? We're going to talk about chemical equilibrium in a couple more chapters. I think it's chapter 13. So that sets up a pressure here, a measurable pressure here. Right? You can measure the pressure of that vapor in that phase. And that pressure is dependent upon two things: temperature. The higher the temperature, the higher the pressure, and the nature of the molecule. Okay. Some evaporate more readily than others. Right? There's some things, if I open a container of, I don't know, just water, right? Or something like water, you wouldn't be able to detect it over there very soon. But if I opened a container of, say, ether, it wouldn't take long, you'd smell it over there. Okay, this is another way of expressing the rate of condensation is initially zero. Oops, went the wrong way. The rate is of condensation, in other words, vapor going back to liquid is zero because there's no vapor, right? So it starts off zero, but as you build up more vapor, you get a higher rate of return. And eventually the rate of return equals the rate of evaporation. The rate of evaporation doesn't change. It's dependent upon temperature and the nature of the molecule. But when those two rates are equal, now you have an equilibrium and you have a measurable vapor pressure that's dependent upon temperature. So if you increase the temperature, you get higher, if you decrease, you get lower. And that's what vapor pressure means. When we say vapor pressure, it's an expression of that phenomenon. Okay. And also I'd make the point that this is what's happening on the atomic level, right? We can't see it. What we see is that the liquid will drop to a certain level and won't go anymore, won't change anymore. At that point, you've got equilibrium. So the macroscopic evidence is the liquid stops decreasing, and the microscopic is you've got an equality of condensation versus evaporation rates. So what's the vapor pressure of water at 100 degrees? It's 1 atmosphere, right? If the water is at 100 degrees, well, that's not a good state. We should say if water is boiling and the temperature is 100 degrees, we know the vapor pressure is 1 atmosphere. Okay, here's an example of several. They're kind of like barometers, only the barometer is on the left. The A that's a barometer because what we have up there in the top is a vacuum. That's a barometer. It measures air pressure because there's nothing pushing back on it here. So this distance here from here to here at sea level on average is 760 millimeters of mercury. But if we put something in that vacuum space and let it evaporate, and as long as we have some liquid and some vapor together, then it will exert a certain pressure, vapor pressure, and decrease the height of that column. So what we see is, oh, wrong way. Go. What we see is with water vapor, it's not very volatile. In other words, it only decreases the height of the mercury column by 24 torr, right? And that's reasonable because water is a polar molecule. It's got forces that are restricting its movement from liquid to vapor at a given temperature. So it should have a very low vapor pressure, and it does. But for something like ethanol, right? Right here, here. That's the drinking kind, alcohol. It has a higher vapor pressure because while it is a polar molecule, its polarity is much less than water, right? So it has a higher vapor pressure, and its vapor pressure is 65 torr at this is probably 25 degrees Celsius. Whereas ether, which coincidentally, well, this is diethyl ether. That's the kind of ether they used to use to put you to sleep for operations. Is a very, very high vapor pressure because it's a nonpolar molecule And at any given temperature, it's going to have a much, much higher push to leave the surface of the liquid. There's nothing holding it back. So that's the relationship between molecular dipole, should say. Yeah, the relationship between dipole and vapor pressure. As the strength of the dipole decreases, the vapor pressure increases. Or if you have nonpolar, completely nonpolar, then vapor pressure is going to go through the roof at any given temperature. Okay, so what we're saying is that liquids where the intermolecular forces are large have relatively low vapor pressure. So they're inversely proportional. You get the intermolecular forces, as they increase, vapor pressure decreases. And the vapor pressure will significantly increase with temperature. Here's an example. Right, so you have temperature on the x-axis, vapor pressure on the y-axis, and you have three different compounds to choose from. Right, so we have water here, right? As we increase the temperature, its vapor pressure increases. It's not linear. Right. Somebody's hungry. That come from a computer? Okay. Ethanol has a lower dipole, so it has a curve that notice it's becoming more and more linear. Diethyl ether is almost a straight line. As you increase the temperature, its vapor pressure goes way up. There are other things with ether that can be nasty too. If you ever use ether, it comes in a metal can and it's sealed when it arrives. And it's sealed with an inert atmosphere, usually nitrogen flushing in the space above it. The reason is you don't want any oxygen, because oxygen will form peroxides, epoxides with the ether, and they're very unstable and explosive, right? And they will form solids around the cap. So if you find an old can of ether and it's got a white solid around the cap, back off. Because all it takes is just a little bump and it'll blow. So whenever we used ether in the lab, we dispense how much we needed, and then we would take the nitrogen line and flush it out before we capped it. And we kept it in a refrigerator too. That slows down the process. Okay. So this is, I think, what equation is this? Arrhenius, I think. Did I put these out of order? No, Clausius-Clapeyron. Okay. Let's go back to here. The expression of pressure is related to temperature, and you can see that in the first equation here. This is the vapor pressure, and it's related, this is E, right? That special number, 2.303, something, something, something. And it's the base of natural logs. That raised to the power of the enthalpy of vaporization minus the enthalpy of vaporization divided by the gas constant and temperature in Kelvin. So there's your relationship between temperature and this enthalpy of vaporization is characteristic of the molecule. So there we have both of those factors in this equation, a mathematical expression for determining the vapor pressure if we know the enthalpy of vaporization and the temperature. So those two relationships are how much kinetic energy, what's the temperature, and what's the nature of the molecule. The enthalpy tells us that. But that's not a very useful equation because we don't know what A is. Right? So we integrate the equation, rearrange it, and now we've got an equation that looks like this down here. The natural log of vapor pressure equals minus the enthalpy over the rate constant times 1/T plus some y-intercept. That's a straight line. So if you do 2 or more experiments where you determine the vapor pressure at a given temperature, then you can extract the slope of that line here will give you the vapor pressure. I mean, the enthalpy of vaporization. That's how it's often determined. You just conduct 2 or more experiments at different temperatures and measure the vapor pressure and plug it in that formula. Well, actually plot it, get the slope of the line, and it's related to that part of the equation right there. And that slope will tell you what the vapor pressure is. Okay. I don't know if I have one of those problems in there or not. Probably do. Give you a little practice. Okay, so there's a straight line, and there's a plot of 1/temperature versus the natural log of the vapor pressure. That's what you have to plot, right? Y equals mx plus b. Remember, I said from the very beginning, scientists don't like curves. We can get away from them. We try to make straight lines out of everything because they're well behaved, right? We can also rearrange the equation if we have 2 temperatures and 2 vapor pressures determined. We can use this modification of the equation called the Clausius-Clapeyron equation. And if you know the vapor pressure, here, this first vapor pressure and its temperature, and you know the second vapor pressure and its temperature, you just plug those values in and you can calculate the enthalpy there. Or it's like any other equation. We've got 1, 2, 3, 4, 5 variables in that equation. If you know 4 of them, you can calculate the 5th. Okay. Oh, okay. So we're going to be given vapor pressure of water at 25 is 23.8 torr. Heat of vaporization at 25 is 43.9. Calculate the vapor pressure of water at 65. So there we're given enough information. I'm not going to try to solve this one on the board. You use that Clausius-Clapeyron equation, and you've got what I will do this much. If you have T1 and vapor pressure 1 and T2 and vapor pressure 2, and you have delta H, those are our values, plus R is a constant, so we won't put that up there. We're given at 25 degrees. Let's see. The heat of vaporization at 25 is 43.9. So 43.9. And temperatures are the same. Then you have to add 273 to it. And then the pressure at this one, at the first one, is 23.8. So this temperature is 23.8 torr. And then this is our unknown. So you plug it in the Clausius-Clapeyron equation, and you get 195 torr would be the vapor pressure. Oh, excuse me, 65. I'm sorry. We did change the temperature. 65 plus 273. There we go. So this would be the pressure associated with that temperature. If we know this temperature and that pressure plus the heat of vaporization, then we can calculate the expected pressure. That's probably the type of problem you'll see in it. Okay. So this is what's known as a phase change curve. We have temperature on the y-axis and heat added at some constant rate on the x-axis. This could be temperature, right? Increase. No, temperature is on the y-axis. This would be I don't know, kilojoules of heat added per second, something like that. So as you add heat, you'll notice that you're starting off with a solid ice, right, from minus 20 C up to 0. So up to 0, where's the heat going? The heat's going into the ice only, and it's just heating up the ice. It's increasing the vibrational kinetic energy of the ice molecules, all right, the water molecules in the ice structure. Once we get to 0, then we put enough heat into it to start breaking the bonds that are holding those snowflakes together. And when we do that, now all the heat is going into not changing the temperature of the solid here, but going into breaking the rest of those bonds. So we're not changing the temperature anymore. As long as there's ice and water together, it will be 0 degrees Celsius and not move until all the solid is gone and we've used all the energy to break those bonds. Now we've got liquid, and any heat we add is going to increase the kinetic energy of the liquid water molecules. And it gradually increases in temperature as we add heat until we get to form steam at 100 degrees C. And at this point, we're doing the same thing. We're breaking the intermolecular bonds that are holding the water molecules together in the liquid phase and making steam. And all the energy we put into it is going to breaking those intermolecular bonds until there's nothing left of the water, of the liquid. At this point, go over here. At this point, we've got superheated steam. And all the energy we add heats up the steam further. That's a general trend for any phase change from solid, liquid, gas. Okay. And you can use that information to solve problems and to tell and to know whether or not you have ice only, water only, steam only, or a mixture of water and steam or ice and water. Okay. Upset tummy. If it was me, I know it's time for lunch. Okay, which would you predict should be larger for a given substance? The heat of vaporization or the heat of fusion? Okay, we didn't define that yet. Heat of fusion is the heat required in usually kilojoules per mole of solid to liquid. Okay, so it's the amount of heat per mole of solid to change it into a liquid. That's what the heat of fusion is. Fusion refers to bigger. Huh? I would say fusion will be bigger. Well, think about it first. Well, let's get them up here both. This is vaporization. It's the same concept, only now you're going from liquid to gas. Okay. Now think about what do you have to do to change a solid to a liquid? Right? Well, on the molecular level, what happens? What's holding solid? There are strong forces holding the molecules in a rigid structure. So to make a liquid, you just need to move them apart, right? Add enough energy to break those intermolecular bonds temporarily so they can slide past one another. Right? So that takes a certain amount of energy. If you're going from liquid to gas, what do you have to do? Well, now you've got the liquid, but now you've got to add enough energy to get those molecules far apart from each other and moving really fast. Right? So this one should be the higher energy. Let's see, do I give an explanation? No, I don't. Sometimes I do, sometimes I don't.
You explained it though.
So this is called heat of fusion because it's thinking in the reverse, right, going from liquid to solid. This is the amount of heat that would be given up as it goes from liquid to solid. It's an exothermic process. But if we use our model, like we did last semester, right? Did we talk about this system surroundings? Yeah. Okay. Then if you add heat to the system, it's going to go from solid to liquid. Right, so the value, the delta H of fusion should be positive value.
That's in that.
And a 30, yes. Okay. Another convenient way to represent substances and their phase changes is called a phase diagram. And I'm going to identify these three components of the phase diagram in the next slide. The triple point, the critical point, and the phase equilibrium lines. Those are characteristic of all phase diagrams. And what they do is they relate temperature and pressure. Okay, so in this case, we have temperature on the x-axis and we have pressure on the y-axis. And if we follow those to where we've identified a temperature and a pressure, we follow those together, and where they meet, wherever they meet, let's say we're here, minus 78 degrees, and we're say 5 atmospheres, right? You're going to be in the solid range. Okay. Or if you're actually at 1 atmosphere at 78 degrees, you've got both solid and gas together, right? I was going to say this is probably carbon dioxide, and there it is. That's carbon dioxide. 78.5 degrees actually is the sublimation point for carbon dioxide. So if you drop a block of dry ice on the table and you get your thermometer and you put it right on the surface, then it should read, if it's capable, minus 78.5 degrees. And if the air pressure is 1 atmosphere, that's another variable. So what we've got here is this phase arrangement in the diagram, where temperature's on this scale, pressure's on this scale, and it can vary all over the place. It depends on the material. It can go like that, it can go like this. And if you see one just like that, typically this represents is solid will be here, liquid will be here, and gas will be there. Okay. Now, these are phase lines, and they show the temperature and pressure at any given point at which you've got both these phases together at the same time. Okay, so liquid and gas would be together at this temperature and this pressure. If you increase the temperature a little more at that pressure, you're nothing but gas. Or if you, at that pressure, or at that temperature, you increase the pressure, now you've got liquid. Okay, that's the way you read it. There's one point in here, right here, that's the triple point. At that particular temperature and pressure, you've got all three phases together, solid, liquid, and gas. And then there's one other one. If you go far enough out here, at a high enough temperature and high enough pressure, that's the critical point. What that means is that at any temperature or pressure beyond, out in this region, you're not going to be able to tell the difference between liquid or gas. It's going to be a fluid, right? It flows. It's not a solid, but you won't know whether it's liquid or gas. And there, you can look this up on the internet, and they show you microscopic views of a transparent tube with a substance in it, and they go through. I don't know if they increase the temperature and pressure both at the same time, or they just hold this one. Maybe they got the temperature way out here and they increase the pressure until it gets beyond the critical point. And you can see, to begin with, you can see liquid and gas in there. You can see the phase differences, and then they gradually fade. the line between the two fades until it's gone. And at that point, you don't know, you can't call it a liquid, you can't call it a gas. It's a supercritical fluid. We used to use supercritical fluid for extraction purposes. You can use almost anything, but our system used carbon dioxide. So you take carbon dioxide and you heat it up and you increase the pressure and you get it past this point, you have a supercritical fluid now, and the supercritical fluids have some interesting physical characteristics. For our purposes, they penetrate plant tissue cells very efficient. They just go right in there. They dissolve whatever's in there and bring it out. And then all you have to do is extract that, bring that supercritical fluid over to another vessel, leave the slough behind, and then release the pressure. Carbon dioxide goes whoop, and you're left with your pure extract in the container. And it does not damage the molecular structure. So say you're looking for a very complicated certain type of molecular structure, and you don't want to damage it with excess heat, which is one way of extracting it with, say, methanol reflux. That take too long to explain it, but if it's a very sensitive molecule, you want to bring it out with as little damage as possible, and that's one way to do it. So those are the, we've got the phase regions, we've got the phase lines, we got the triple point, and we've got the critical point. Those are characteristic. Now, these phase diagrams can be very complex. In other words, you can have not just solid, liquid, and gas, but you can have a certain type of solid structure. And then another allotrope of that solid would give you a different phase line, right? So these things can get extremely complicated. And that's where chemical engineers have to, that's where their bread and butter is. But normally, this line right here between solid and liquid has a positive slope, like that. So if you're at a certain temperature and you increase the pressure, you can go from gas to liquid to solid. Right? You can go like that. Water's different. Water, this line has a negative slope. It goes back like that. So at a given temperature, you can go from gas to solid and then back to liquid. It's strange. That for the longest time was an explanation for why ice skaters could move, could slide without having rolling wheels, right? You put all your weight on that thin blade, it increases the pressure so high that you actually, between the ice and your blade, you have a layer of liquid water. Now, that's since been disproved, but it's a nice theory.
Service instruments up.
Probably something like that, yeah. Or the coefficient of friction of ice against steel is very, very low to begin with. So maybe you don't need it after all. Okay, so I spent too much time on it. And this is an illustration of that effect. So if you see a diagram where the solid liquid phase line is tilted back the other way, probably water. I'm sure there are other compounds that will do that, other substances that will do that, but they're not very common. So if you see one, it's a safe bet that we're talking about water. Okay, so if we look at these different properties of a substance, and we want to relate them to intermolecular forces, what we want to do is say, for this problem, we say, as the strength of the intermolecular force increases, what happens to each of these properties? So think about what is happening with the boiling point. What does it have to do? it has to break those bonds, right? So if the strength of the bond increases, the boiling point is going to be higher. You got to add more energy. So you should have to increase the boiling point. Yeah. How about viscosity? Right. If the strength increases, the viscosity increases. True. Now surface tension. Increase. Right. If you get an increase in strength of attraction between molecules, it's going to increase the surface tension. Yeah. How about enthalpy of fusion? That should also increase. Right. If you got to overcome more force, you got to put more heat in. Freezing point. Should increase also. Vapor pressure would decrease though. Yeah. Pressure should decrease. And heat of vaporization should be like heat of fusion. So the only one that decreases with increasing intermolecular force is vapor pressure. The rest of them increase. Okay, that's it for chapter 10. By now, actually, the only student that would benefit from all of these is Halliana, because she hasn't had me before in chemistry.
Can I get those from you when we have our first lab?
Sure.
Okay, thank you.
Yeah. They're also in bright space.
Oh, okay, thank you.
You want to get ahead of the game there. Maybe what I ought to do is show you each one of them. Because it can get kind of confusing when you get into bright space and try to figure out which ones I handed out. They're all there, but it might be difficult figuring that out. Let me just, we'll do one at a time, and I'll show you what they look like. Okay, well, the syllabus, right? There's your syllabus. And then there should be a blank rubric. This is what I use to grade formal reports. And then safety contract will look like this. And it has two sheets on the back that you'll fill out. Looks like that.
Okay.
The only reason there are two sheets in there so you can fill it out and hand me one and you keep one and you know what you told me in your contract. This one is a sample lab notebook. So it's laid out the way I want to see it and gives you a sample of works. The only problem is, well, I guess that's all right. We'll maybe I better talk about that in just a minute, right? Because you'll want to get started. Or did I talk about that last time? I didn't, did I? About how to set up your notebook. Because you guys already knew.
Yeah.
I didn't talk about that. Okay, so maybe I'll spend just a few minutes and talk about that now, because it'll take you a little bit for the first time getting it set up. This document is what constitutes plagiarism in a lab report. Right? It might be a little cryptic. Plagiarism in like an English paper or thesis is pretty easy to fathom. You just don't want to quote somebody without giving them credit, basically. but lab is a little more tricky. This particular document is my extended character set document. And in order to get these special characters that you might need in a lab report, instead of going to the character map and finding them and copying and then pasting into your document, which takes several steps, if you go to the number pad on your computer, assuming you have a number pad on your computer, I don't get one without one, and you hold down the Alt key, and then you type in this combination of this code combination, then most of the times you'll get the special symbol right where in your document where you hit that key combination. So it can save you a lot of time. This is a document on the report format. It helps you organize your report. And actually, your lab notebook, if you set up your lab notebook with this format, then writing the report is much simpler.
Okay.
And then to try to make it even simpler, I've got a sample report with a graded rubric on it. And you can see some of the stuff in here that this particular student, actually you can see some mistakes too, and you can see some of the better arrangements of information. This one's a good one. Common errors and guidance for preparing a formal lab report. These are the types of errors that I see, that I've seen over the years in lab reports. And this can help you avoid those errors, because those types of errors will cost you points. And then this is the first lab, molar mass by freezing point depression. We're going to cover freezing point depression in chapter 11 in just a minute. That's why I wanted to get it done before we talked about the lab, because then it would make more sense. Okay, so those are the ones that I handed out today.
Okay, thank you.
So chapter 11 is all on the properties of solutions. Get out of the way. And it's going to get funky on me, isn't it? There it goes. All right. Different types of solution. Remember, a solution is a homogeneous mixture. And as a mixture, all the components retain their chemical identity. They can be separated from one another using various physical means. But they can be made, they can be built, they can be constructed from different phases. Right? The air we breathe is a solution. It's a solution of primarily nitrogen and oxygen, 78% nitrogen, 21% oxygen, and 1% other stuff. So when we put two or more gases together, we end up with a gas phase as the solution. We can form solutions of two or more liquids, right? All alcoholic beverages are at least water and ethanol. Antifreeze in your radiator is water and ethylene glycol, which is also a liquid. And you get a liquid out of mixing two liquids together. You can have a solution, a solid solution. We talked about brass earlier, where you put copper and nickel together, but you can't just lay them together and make a solution. Right? You got to heat them up. This is also an alloy. And you've got a solid formed from two solids, but you have to sort of go through some gyrations to get them together, right? Heat them up, and then they can re-solidify. Carbonated water is a liquid, but it's formed from water, which is a liquid, and carbon dioxide, which is a gas. Right, so you can dissolve gases in liquids and make a solution. The more traditionally understood solutions are solids and liquids. like salt in water, sugar in water. Seawater is a good example of a liquid that's formed from a solid and a liquid. You can also have solutions of a gas in a solid. Processing, let's see, which example do I want to use? If you process, well, let's use the exhaust from your automobile engine. The way that we use in this country to complete the reaction process so that we expel nitrogen, carbon dioxide, and water out the tailpipe is we pass the exhaust from your engine over a catalyst, platinum. Well, actually, it's platinum and palladium that's coated on ceramic beads. Actually, used to be ceramic beads, so pardon me, ceramic matrix of some kind. But in the process of undergoing catalysis, these compounds, the gas actually diffuses into the solid, the platinum in this case, and before the reaction takes place. So at least for the time that the gas enters the solid, you have a solution of a gas in a solid. The chemical industry uses this type of arrangement for processing petroleum. In addition to distillation, like they'll take a barrel of oil and run it through a still and separate its components by boiling point, and then they may want to further process it. Well, they could take the oil and they mix in with it gas of some kind and pass it over a catalyst. And in that case, you have several types of solutions in a very complex mixture. So we need an expression, a way of expressing, since mixtures, in this case solutions, can have variable composition. In other words, you can have a solvent, right? How many solvents can you have in a solution? Only one solvent, but you can have several solutes. These are the minor components. This is the major component. So you can have lots of solutes, but only one solvent. And since it's a mixture, and these components retain their identity, they can have variable composition. In other words, you can have very small amounts of solute in the solvent or very large amounts of solutes in the solvent. We need a way of expressing that concentration. And these are different ways to express it there on that in that slide. Molarity is very common. Have we talked about this before?
We talked about polarity last session.
Okay, so I don't have to beat this one too hard. Molarity then, if you remember, is moles of solute per liter of solution. Okay, and that can vary. Weight percent, right, is just what it says. Or actually, it's more accurately mass percent. It would be so many percent mass, which means the solute is in terms of mass and the solvents in terms of mass. And this expression would be mass of solute per 100 units, let's say grams mass per 100 grams of solution. So if you have 100 grams of the solution, and this can be anything, liquid, gas, liquid, solid, 100 grams, then this number will tell you how many of those grams is the solute. So a 10% would be 10 grams of solute in 100 grams total mass of the solution. Molality is like molarity, only it's a little m. And it's related, similar to this, in that it's moles of solute but this changes per kilogram of solvent. So two things change. One is instead of volume, it's mass, and instead of total solution, it's only the solvent. Okay. We use this expression, and we're going to use this relationship in our lab because we're going to use freezing point depression, which incorporates an expression of concentration as a variable with temperature. And if temperature changes, what happens to volume? Volume changes. So we can't use molarity in that expression because as the temperature changes, the volume is going to change and this concentration will change. So instead we use molality because its expression is terms of mass and that won't change with temperature. Okay, it'll be much clearer after you read the lab and we talk about it on Tuesday. But that's where we're going to use it. Mole fraction. Mole fraction is this big X, and the mole fraction is equal to moles of some solute X per total moles. Sorry about that. Solution. Okay,
Let's talk about financial aid.
I figured somebody collared you. Total moles of solution, and then how many of those moles are that component, right? So actually, mole fraction could be an expression for the mole fraction of the solvent as well. If you have two components, and you say you have 10 moles of X, and you have, that's a bad choice. Confusing things. Let's call that A. Moles of A. If you have 10 moles of A and you have 90 moles of B, then the mole fraction would be what? The total moles is 100, right? So this would be 10 divided by 100, which is equal to 0.1. The mole fraction of the solvent would be 0.9. So when you get the mole fractions of all of the components and add them together, they're going to be within experimental error equal to 1. And it's just what it says. It's a mole fraction. Oh, I skipped that one to get down to molality, didn't I? Okay, so everything's up there. Those are the most common expressions for concentrations of solutions. Mole solute per liter of solution. The nice thing about molarity is that you can extract, if you have a solution and you know the concentration in molarity, then you can extract a certain volume from it, and by calculation, you know exactly how much solute you possess in that sample. We'll do some calculations in a minute. Okay, so if we're going to calculate what? Molarity. Calculate molarity for this solution. It's actually like any formula. Like density is M divided by V. Molarity equals moles, and that's my abbreviation for moles, per unit volume. And the volume has to be in liters. So there you have a formula. What are we given? 1 mole of sugar. All right, so we have 1 mole here. In what volume? 125 milliliters. All right, so 125 milliliters is how many liters? Right. 1, 2, 3. 0.125 liters. So we divide 0.125 into 1, and that's going to be a number greater than 1, obviously. It'll be 8 molar. And that's the way you would express it. Let's see. 1, 2, 3, 1, 2, 3. So 1, 2, 3 molar sugar. Okay. All right. Let's take it another step. Suppose we have we know the concentration is 10 molar. Right? And that's equal to, we want to know what volume of this solution would give you 2 moles of sugar. Right? 2 moles. And the unknown is the volume. Right? So you solve for your unknown. So this comes over here, that goes over there. V is 2 divided by 10, which is 1/5, or out of 0.2. 3 significant figures. And that's liters. You have to remember that's liters when you're talking molarity. Okay. Just out of curiosity, how many milliliters would that be?
0.002.
Wrong direction.
2.20.
200.
200.
Yeah.
I knew they were right.
Remember, if you're going to make the unit smaller, that has to get bigger. So that can, help keep you straight. You have to move the decimal. Since there are 1,000 milliliters in a liter, tens, hundreds, thousands, 200 milliliters. Okay. Let's see, what do we got here? Consider separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each in 250 milliliters of solution. What's the concentration of each? Okay, so I'm going to use Henry Ford here. We've got sodium hydroxide is one solution, potassium chloride is another solution. Okay. And we've got 100 grams of each. Oops, force it. Here we go. 100 grams of each. And we want to put them in 250 milliliters. Well, we know in liters that would be 0.250. 0.250. So we know what the volume is. We need to know the moles of each, right? Are the moles going to be the same? Short answer is no, because they have different molar masses. Right? You need to know moles. You don't need to know mass. So we need to convert each one of these to moles. Right? Grams on the bottom, moles on top. So we need a special number for each one. Sodium hydroxide would be what? Let's see, sodium is 23. Yeah, 23.00. So this is 23. Oxygen is 16. Hydrogen is 1.01. So that's 40.01. Okay. How about potassium chloride? And then we go back to our 39.10 for potassium and 35.45 for chlorine. And that would be 5 and 4 and 7. I think I did that right. So now all we need to do is divide 100 by 40. 40.01. And that's 2.499. 2.499 moles of sodium hydroxide. And this one is going to be different. 74.55. This one is 1.341 moles. Okay, so now we have volume and moles. We just need to calculate for sodium hydroxide. This would be 2.499 moles per 0.2500 liters. Let's see, 0.25. Okay, that's going to round to 10.00 molarity. And potassium chloride should be less, shouldn't it? it's fewer moles per 0.2500 liters. So let me see. So I'm still in my computer, 0.25. So this is 5.366. Okay. Yeah, they rounded it to 3. That's cheating because we got 4 significant figures. Okay, so the point of that slide is grams doesn't tell the whole story. You got to have moles before you can satisfy the conditions for calculating molarity. All right. Mass percent, that's even easier. All right, so what would be the mass percent of 5.5 grams of glucose in 78.2 grams of water? So the glucose is 5.5 grams and water is 78.2 grams. Okay, so the mass percent is equal to what? Well, put that one in the numerator. What goes in the denominator? Plus 5.5. Because it's the total. It's the total mass. And then times 100, because this is percent. And that should come out to 6.6%. I'm not going to risk trying to calculate it myself. Right. Now that was a solution. But you can use mass percent also for solid mixtures. And so if we have a sample, an ore sample, say, and we've got so much copper in that ore, and they send it to the lab, sample sent to the lab, and they report it, they're going to report it in percent. A percent mass of copper per mass of the sample. And then they can use that to decide whether or not the ore is worth going for. They run their calculations and see if it costs more to get it than they'll get back on the market value. Mole fraction, right? We went over that one before. A solution of phosphoric acid was made by dissolving 8 grams of H3PO4, grams of H3PO4 in 100 milliliters of water. So, yeah, places, milliliters of water. And we want to know the mole fraction. And we assume the density of water is 1 gram per milliliter. Why? Because there's no relationship between volume and mass. There's no relationship between moles and volume. There's a relationship between moles and mass. So this has to be converted to mass. That's why they told us 1 gram per milliliter. So if you got 100 milliliters, how many grams you got? Right. So now we can calculate the moles of each. So the moles of phosphoric acid, we need a molar mass of phosphoric acid. Right. So 3 times 1.01 for the hydrogen. Then phosphorus is 30.97. 7. And we have 4 oxygens times 16. There we go. Oops, what did I do for series? All right, so hydrogen's 3.03, 30.97 for phosphorus, and 64 for oxygen. It's 98.00. I've already got it in here, so I'm going to divide that into 8. So it's 8.16 times 10 to the minus 2 moles. How many moles of water do we have? Well, we need. Anybody remember the molar mass of water? 18.02. Right, 16 for oxygen and 2.02 for the hydrogens. So 100. I'm sorry.
Said, I shouldn't have.
Oh, okay. 5.55 moles of water. Okay, so the mole fraction is the total moles would be down here, 8.16 times 10 to the minus 2, which wouldn't change. Well, it will change a little bit. Plus 5.55, this is the total. Right, and the moles of H3PO4 is in the numerator also. And we don't multiply by 100 because this is fraction. So 8.16, that, and let's see. And those together.
What is mean 5.55?
Pretty close. 5.63.
Oh,
8.16 exponent minus 2.
I just think slow.
They would if it were multiplied. This is addition. Okay. So this one together is 5.63. Divide that by this one. 8.16 exponent 2. And we swap those and divide. Okay, here we go. 1.4445 times 10 to the minus 2. If we put that in standard notation, we move this to the left 2 places. Okay. 1, 2, that's right. That's mole fraction of H3PO4. Okay. So what would the mole fraction be of water? The 1 minus that. 0.986. 8 and 55. Mole fraction water. Add those together, you get 1. Okay. All right. So let's say molality. Okay. I was explaining to the class, molality is the one we're going to focus on for our first lab. Okay, solution of phosphoric acid. Oh, did anybody write that down? I'm gonna have to do it again. 8 grams of phosphoric acid. We need to know the moles of 8 grams of phosphoric acid. Okay. We'll just do it again. Phosphoric acid, 3 hydrogens, 3.03. Phosphorus is 30.97. And 64 oxygen.
98 on 0.
Yes. Okay. So we divide that into 8. And we get 8.16.
That's negative
2 moles. Okay, now we know the moles of our solute. Calculate the molality in 100 milliliters of water, which would be 100 grams. How many kilograms is that? Because the expression is moles of solute per kilogram of solvent.
Would be 0.100.
Right. This is going to be getting bigger, so the number has to get smaller. Right? Tens, hundreds, thousands. kilograms. Okay, so now we can calculate the molality. 8.16 times 10 to the minus 2 divided by 0.1000, which would be 8.16 times 10 to the minus 1, right? Because this is 10 to the minus 1, becomes a positive up here, changes that one to minus 1. So this is 0.816 molality, I think. Yeah. Okay. Now what? Oh, okay. We're going to have to use our imagination here. When a solution forms, and it's okay if you want to think of this in terms of a solid dissolving in a liquid like salt in water, if it simplifies the process. We're trying to understand what's happening. Now, we know all this stuff happens almost simultaneously, but if we try to visualize it, we extract these three processes that must go on in order for a solution to form. Okay. So if we have a solute and a solid, the first two things that have to happen is separate molecules. You got to pull these molecules apart. Okay, and that is an endothermic process. So delta H is going to be positive. Same thing happens over here. Solvent, in this second step, you separate molecules. That could be atoms too, depends. This is also endothermic. You have to put energy in to get them apart. Okay? You're overcoming the intermolecular forces. Sometimes this is called make a hole. Okay? Bust these apart, make a hole, and then the third step is you form a bond between the solute and the solvents. The intermolecular forces then take over. You allow the solvent and the solute to bond. Now, that's not saying we form a covalent bond or an ionic bond necessary, maybe dipole-dipole. It could be London dispersion, it could be ion dipole. Any one of those are possible. And this one is exothermic. Okay. Now, whether or not this process, once it's complete, and all of your solute is in solution, the overall delta H for the solution could either be negative or positive. And that's based upon the balance. How much energy did you have to put in, and how much did you get back? And that will determine whether it's endothermic or exothermic overall. So these hot packs and cold packs you get in the hospital, some of them you break that little capsule inside and mix it up. Some of them get cold, some of them get hot. So the ones that get hot are the ones that have this step produces more energy out than you had to put in. And the cold pack is the other way around. You get less back than you put in. And that manifests itself as an overall endothermic process. And that's your publisher's idea of the explanation. That the formula is valid though. So the overall delta H here is the delta H responsible for this step plus the delta H for the second step plus the delta H for the third step. And that's equal to heat of solution. I know it's a long day. This just beats the horse again. That horse is already dead. It says the same thing I said here in black and white. And that also says, right, it's the summation of the different delta H's. All right, let me put this delta H1, this is 2, this is 3. Add them all together, and that determines the overall heated solution. And this is a pictorial description. Delta H and delta H1 and 2 would be adding energy into the system, and then delta H3 would be getting it back. And the balance here determines whether it's you get a lot of energy back for exothermic, you don't get as much back for endothermic. Okay, explain why water and oil do not mix. And we want to do this in terms of these various heat steps. Let me see. I guess I have to do that one freehand. Okay, water is polar. Right, so water would be the solvent. Let's just arbitrarily say water is the solvent and oil is the solute. Okay. How much energy is it going to take to get these things apart? A lot. Large. So this would be for this particular molecule, this would be large. For this step for the oil, this would be small. Right? Because the only thing holding them together is London dispersion forces. Right? How about this one? Are you going to get anything back? This is a polar, this is a non-polar. How do they interact? Well, if I didn't say it before, London dispersion forces are always there. It's just that if there are dipole moments, then the London dispersions are so weak it don't matter. But they are always there. And that means the only interaction that water and oil can have is through London dispersions. Okay, and since they're very weak, this amount of energy that you get back is very small. Okay, but when we add those all together, this negative is small. Maybe it's approximately the same as this one, right? And actually, it's probably smaller. So let's say these, excuse me.
The end results will be positive.
So the end result is going to be positive. It means you have to put a lot of energy in to get anything to happen. So the conclusion is that this solution is not going to form readily at low temperatures. There's not enough energy to do it. So have you ever seen a dirty automobile engine steam cleaned? Yeah. The guy wears these big gauntlets, you know, and face coverings and maybe a coat. And he's got this hose coming to this big wand thing with a trigger on it. And he goes in there and he bathes that engine in steam. And well, several things happen. One is the force of the steam coming out of there just blows the big particles off. But you got to get down in little cracks and get the oil out of there because it carries with it dirt also and corrosives. So the heat from the steam will melt and liquefy the oil, but that doesn't explain the complete cleaning of the engine. Actually, at those high temperatures, you do have enough energy here to form a solution of water and oil. And just long enough to get that solution to drip off the engine. And then once it hits the ground and cools down, they separate again. Okay. So typically you don't form solutions between polar and non-polar materials. That's where the expression like dissolves like comes in. Polars dissolve polars, like water can dissolve ionic compounds and polars. sugar is polar, sodium chloride is ionic, and they go into solution very, very easily. But oil doesn't dissolve in water. Now, if we had some other non-polar solvent up here, that would be low value here, low value there, and low value there, then you would get a solution. Because at this temperature, the overall delta H would be small. It wouldn't need a lot of energy, or it wouldn't get a lot back. I mean, it's very close. You tend to do form solutions. And I think the next table puts those in all together. So across the top, you'll see you see the delta H1, delta H2, 3, and the overall. So you add these all together and you get this value. Okay. So the first possibility is polar solute and polar solvent. Both of them, the solute and the solvent, take a lot of energy, right? But when they slam back together, you get a large amount of heat back. So the delta H of solution would be small. And there's the key. If the delta H is small, then you're more likely to form the solution. The other possibility is if we go down to nonpolar here, where the delta H1 and 2 are small, but the delta H3 is also small, and the difference is small, and you get a solution for it. But if you have a nonpolar solute, a polar solvent, the gap is too big. You get a large positive value for one, no solution. You get a large positive value for the other one also, and no solution. Okay. So there's an attempt to try to explain why like dissolves like is a valid rule of thumb. And to take up a few more pages in your textbook. Okay. These are factors that favor a process that will produce a solution. The first one we see here is if we have an increase in the probability of a state when the solute and solvent are mixed. So what does that mean? Well, if we go back to our discussion of oh, have we done? Did we do that? Hold on a second. I don't want to steal my own thunder. Ooh, no, we haven't talked about that yet. Okay, so let's just leave it at that. We're speaking in terms of probabilities. If we increase the probability of something occurring, then it's more likely to occur. I'll just leave it at that for now. We'll talk about that later. I think chapter 17. We get into entropy, and then we talk about probabilities big time then. Processes that need large amounts of energy tend not to occur. Okay, so there it is. You can't dissolve oil until you get that steam really hot. And then this all boils down to that rule of thumb, like dissolves like. And that refers to polarity only. Okay. So we've talked about structural effects of molecules in terms of their polarity. So we don't have to talk about that one, except in terms of how it affects the formation of a solution. But we've also got some other things we can talk about. What are pressure effects of these various factors on solutions? In other words, if we have a two-component mixture, a solvent and a solute, and one of the solvents, the solute is a gas, then Henry's law will address the concentration of the gas in that solution based upon the pressure over the head. Okay, so if you increase the pressure of the gas in the headspace, then you'll get more of it in solution. Right? That's kind of intuitive, actually. And then we're going to look at temperature effects. What effect does temperature have on aqueous solutions? All right, so the structural effects, but we've talked about polar versus non-polar and like dissolves like. There's another term that's often used, hydrophobic versus hydrophilic. Hydrophobic generally means non-polar relative to water. And hydrophobic just means water fearing. Hydro is water and phobic is the Greek term for fear. And then hydrophilics are water loving, that is, they're polar or even ionic. Here's Henry's law. In Henry's law, it says that the concentration of the gas in solution is proportional to the pressure. And it uses subscript. No, it doesn't. And we would say here the partial pressure. The reason we say partial pressure is it might be a mixture of more than one gas. And this formula works for each individual gas. So at a given pressure, one gas might go into solution to a large extent and another gas might to a lesser extent. And that's based upon its partial pressure. So if we have, say, nitrogen and oxygen, right, breathing air, at a given pressure, you're going to get more nitrogen dissolved in your body tissues if you're a scuba diver, more nitrogen than you do oxygen, because the concentration of the partial pressure at 1 atmosphere, or, well, if you're going deeper, you want more than that, say 3 or 4 or 5 atmospheres in your tank, or coming out of the regulator, the partial pressure of nitrogen is going to be about 80% of that total. So if it's 2 atmospheres, it's going to be like 1.6 atmospheres. But oxygen is only going to be 0.4 atmospheres. So it's going to go into your tissues at a lower concentration than nitrogen does. So that's why when you go deep and you get nitrogen dissolved into your tissues, you're not using it. Right? Your body's not using it and metabolizing it. It just goes into your tissues. Then if you come up too fast, decrease the pressure, it's going to come out of solution. And where it tends to come out of solution is in nasty places. Right? The most painful, of course, is probably your joints. And it'll come out of solution in your lungs. It'll cause air embolisms in your blood vessels. Right? So if you come up too fast, the bends can and often does kill you. Unless they put you straight into a hyperbaric chamber, get the pressure back up, and then gradually decrease it to let the gas come out slowly on its own.
That's great.
That's why if divers are going to go really deep for long times, they have a special mixture that has no nitrogen in it, and the balance of the gas is helium instead, because helium does not dissolve readily in tissues. It's very low solution factor. But also makes you sound funny. Okay, so that's Henry's law. And this is the explanation. This is supposed to be, let me see if I can show you. Right here, right along that line is the level of the liquid right here. Okay, it's kind of hard to see, but there's liquid there and everything up here is gas. And the gas molecules here, there are no liquid molecules shown. The liquid is just liquid, and we're focusing on those purple spheres are the gas molecules. So as you increase the pressure, you actually decrease the area in that whole headspace. And remember what happens when you decrease the area, increase the pressure. You decrease the volume, increase the pressure. That's Boyle's law. So you're increasing the pressure, and that's due to the kinetic molecular theory, the number of impacts per unit square. Right? Increase the number of impacts per unit square on the surface of liquid, you get more of them in solution. Okay? And they'll stay in solution as long as that pressure is there. So if you buy a bottle of a 2-liter bottle of pop, and you take it home and you're in a hurry. So you get your glass of ice and you crack the top and it goes, you lost a bunch of carbon dioxide. You know, that's one of the attractions of carbonated beverages. So instead, and this is, I'm prefacing a slide to come. You decrease the temperature, you stick it in the fridge and decrease the temperature. At lower temperature, you get more gas dissolved in the liquid. It's an inverse relationship. Decrease the temperature, more higher concentration. If you do that, then when you take it out of the fridge and crack it, it goes, and you don't lose as much. So that's why I hate picnics. They've always got the 2 liter bottles sitting out in the hot sun, and the first person that cracks it gets the most carbonated beverage, and everybody else gets flat. Okay, so here are the temperature effects. Depending on what the solute is. If the solute is a solid, generally speaking, the higher the temperature, the more of the solid will dissolve in aqueous solutions, right? That's where we're focusing on this slide. There are some exceptions to this. Sometimes decreasing the temperature will increase the solubility, but it can't be predicted. Okay. So most solids increase solubility with temperature, but a few go the other way around. Solubility of gases, on the other hand, are relatively uniform. As you increase the temperature, the solubility goes down. And that's largely because when you get gas molecules dissolved in this solution, and you increase the temperature, you increase the kinetic energy of everybody in that solution, right? Including the solid. Solute, you increase the kinetic energy of these. That means they have more energy to escape into the headspace. And when you do that, it increases the vapor pressure, or the pressure due to the dissolved gas, but it also decreases its concentration in the liquid. So you increase the temperature, you decrease the concentration of the dissolved gas. So if you put, you get water out of the tap, put it in a pan, stick it on the stove, and you're going to boil water, right? As it heats up, right? What's the first thing you see? You start to see these little bubbles, right? Those are not water vapor. Those are gases coming out of solution. You can only be sure that what you're producing is water vapor when it starts to boil. Okay. All right. And here is variable solubility with temperature. So you'll notice that sugar behaves itself. Let's see here. Here it is. Sugar, sucrose, C12H22O11. That's sucrose, table sugar. It increases solubility with temperature. Right? It behaves itself. This ionic compound, potassium nitrate, it also increases solubility with temperature. Sodium nitrate does too. Potassium bromide does. Potassium chloride does. But notice sodium sulfate decreases solubility with temperature. And cesium sulfate decreases solubility with temperature. It's not predictable, but it does happen. Now, gases, we find that these gases decrease solubility with temperature, right? Methane, oxygen, carbon monoxide. I'm going to put carbon dioxide in there too. Nitrogen. Helium, though, does decrease solubility with temperature, but it's a very shallow slope. And in fact, it starts off at very low concentrations. So we use this factor in the laboratory to remove dissolved gases from our mobile phases. Mobile phase is that liquid that you drive through your chromatography column. If you've ever seen chromatography columns, some of them about that long, made out of stainless steel, because they've got to stand up to hundreds of atmospheres of pressure. And they're packed with very fine microscopic sized beads in there, various chemical compositions. They're customized if you want. And you put your sample, well, you start driving your mobile phase through them at very high pressure, and then you inject your sample and it moves through that column. And because it's under high pressure and these particles are very small, you get a very efficient separation of components. But when it comes out the other end, before it goes to the detector, and the detectors can vary, the pressure drops to atmospheric. Right? It comes out the other end, it's the same as atmospheric pressure. And under that extreme pressure, once you turn it loose on the other end, any dissolved gases are going to go like that. And if they don't damage your detector, they'll sure mess up its ability to detect your samples. You got all these gas bubbles floating around. So we want our mobile phase to be devoid of gas as much as possible. So one way, the cheapest way, is to sparge it. You've seen these little air stones that you can aerate your aquarium with, right? Put them on the end of the line bubbles through. We put those on the end of a tube and drive helium through them. And they go into our reservoir of mobile phase. And we do that for a while, and the bubbles actually mix the solvent. And while they're in there, they displace the other gases. Right? And helium is very, very low concentration. And it's very innocuous material to begin with. And then when it comes out the other side, we don't see a negative impact on the performance of our detector. The other way to do it is to have this little device with a membrane in it. All right, so here's your membrane. And you got your mobile phase coming in here. And your mobile phase coming out here. And on this side, you can do several things. But what is often done is this is very, 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 very strong and very fine holes. Right? It's a membrane that only has holes big enough for gases to get through. So you drive your mobile phase through here, and actually this goes through before it gets to the high pressure pump. Right? You don't put too much pressure on that membrane, you'll rupture it. And on this side, you have a vacuum. Right? So it tries to set up an equilibrium where the gas comes out of solution, and but there's no head pressure there. So when it comes out, it's gone. And that will degas your mobile phase before it goes to the pumps and into your column. Okay. In fact, most of the newer, this technology is called HPLC, high pressure liquid chromatography. I don't know if you guys are going to get into it or not. But maybe some of your equipment uses that technology inside and they just don't let you see it. Now, this slide illustrates the fact that the two solutions inside this bell jar are trying to reach equilibrium with the vapor phase. So we've got a solution we've got pure water on the left, and then we've got an aqueous solution on the right. And what they don't tell you is this aqueous solution on the right has a non-volatile solute. Right? If it's a volatile solute, then you got to take that into account because it's trying to leave into vapor phase too. But if it doesn't, then what you have is inside that bell jar, you have these two. This is pure water, and there's the solution. And inside the bell jar, we've got this sealed off. So water is evaporating at a certain rate, and it's evaporating here from a certain rate also. But this is a lesser rate. So let's make that a shorter arrow. Why? Because you've got solute molecules that are doing two things. they're a physical hindrance at the surface. Right? You don't have as many water molecules at the surface leaving, and there are intermolecular forces attracting the water by the solute. We know that's true because otherwise the solute wouldn't go into solution. So that reduces the rate of water evaporating. Over here, there's nothing holding it back. This is pure water vapor pressure. Like what was it, 24 or 28 bar? Torr. I think it's 24, yeah. 24 here, it's going to be less over here. So what's happening is you're trying to set up an equilibrium, but this is always evaporating too fast. So this water is going to come over here and it's going to condense there. And it's going to keep doing that until you either establish an equilibrium or all of that water is gone. Okay.
How can you establish an equilibrium if that one never will evaporate at the same rate?
It would take a lot of water.
Yeah.
You take a huge beaker over here and a little tiny beaker over there. I don't know if you would ever. Yeah, that's a good question. It may not ever come to equilibrium. Now, if you had a concentrated solution over here and a less concentrated or dilute solution over here, maybe you could reach equilibrium. But I've seen that line. The best solute to use over here is sulfuric acid. It works great to demonstrate this process. Okay, vapor pressure of solutions. These can be quantified. What is the actual vapor pressure of this guy if you put it in a sealed container of its own? And just forget about that. All right, you got this solution over here. It will produce a vapor pressure less than the pure solvent for the reasons that I gave you. Right? There's attraction, there's interference. You can calculate that. All you need to know is what's the mole fraction of the solvent. Okay. And Rayleigh law will tell you that. So the vapor pressure of the solution is equal to the mole fraction of the solvent plus times the vapor pressure of the pure solvent. Okay. It's really simple. Now, this only works, and let's see, they put that up there for standard conditions. Right? But it'll work as long as the temperature doesn't change, and you know this value and that value, you can calculate that value at any temperature. This formula works if the solute is non-volatile. Because if it's volatile solute as well as the solvent, it's going to add its own component to the vapor pressure. And then you can't do it with this formula. We're going to modify it where you can do it. And this is what it would look like if you plotted them, the mole fraction of the solvent from 0 on the left to 1, which would be pure on the right. And the pure would give you the highest vapor pressure. And the vapor pressure decreases linearly from right to left as you decrease the mole fraction of the solvent. Mole fraction of solvent is 1, it's pure. Right? If it's 0, it's all solute. Right? And then there's no vapor pressure. Now, this is ideal. That straight line relationship, as luck would have it, we're going to show some non-ideal deviations. Unless you've read ahead or looked ahead, you'll see.
Yeah.
Okay, here is the modified Rayleigh's law to take into account other components, volatile solutes. So, in this case, we don't even treat the solvent like that. We just say this is component A and this is component B. So you need to know the vapor pressure of the pure A and the pure B, and then if you can determine the mole fraction of each one, then this relationship, you just add those two components together. It's kind of analogous to Dalton's law of partial pressures, right? The total pressure is due to the individual pressures. And you can add, if you've got more than two factors, you can add them on out there. It can get really complicated. But you should be able to add these two together and get one, or these three together and get one, always. The mole fraction has to add up to one. Okay, so if you only have two components and they're behaving ideally, then you get the graph on the left. And the mole fraction of A increases to the right as the mole fraction of B increases to the left. So they're like complementary. And if you're only doing this one here, A, you'll get the red line. And if you're only doing B, you'll get the blue line. Because as A increases, B decreases. So you should see the B decreasing in vapor pressure as A increases. That's why they run opposite slopes to one another. The vapor pressure of both of them together, you just connect the endpoints of the pure substances. So if you go from pure B down to pure A, you get the green line. And that's any place along there with the different mole fractions, you should be able to find that pressure on that green line. And that is as a result of this calculation. Okay, that's ideal situation. Now, if you get a weak interaction between solute and solvent, then that tends to increase the pressure of A and B, and the subsequent summation of the two gives you convex deviation. Right, so if you have weak solute-solvent interaction, then you get the positive deviation, or the convex deviation. If there is a strong solute and solvent interaction, then you decrease the combined values for each one of these. If there's strong interactions between the two, then you decrease this one, and that one, you also decrease this one, and that gives you a concave deviation. Okay. So I think what we're trying to show on this table is examples on the far right of deviations or ideal behavior, and the relationship of that to the delta H of solution. So if the delta H of solution is near zero, you're going to get an ideal, because the interactions between the individuals molecules here and these here are about the same as when you put them together. You don't get a change in the heat of solution is not much different than the delta H1 that would go into this one, or the delta H2 that would go into that one. They're virtually zero overall. In that case, you would get an ideal solution behavior and no deviation in Rayleigh's law plot. And a good example there is benzene and toluene. Benzene is, well, I drew benzene before. It's like this. And toluene is similar. Only it's got a methyl group on the side. So they're virtually the same, and they're both nonpolar, right? And they'll dissolve in one another, and the delta H is almost zero. So they show an ideal behavior with Rayleigh's law, right? Straight line, straight line, straight line. The next example, where acetone and water are both polar, right? So they have a strong interaction between the solvent and the solute. So we should see the curve dip, right? Should be a concave. So the attraction between the A and A, the acetone and acetone, versus the attraction between water and water, either one of those is less than the attraction between water and acetone. And you find that to be an exothermic, right? Because delta H3 is gives up more energy than you had to put in to get them apart. So that shows you a negative deviation or a concave. Ethanol and hexane, that's the other way around. They show a positive deviation because they don't like each other. They will dissolve. Ethanol will go into hexane to a limited extent. Because I think of it as sort of a repulsion. They don't like each other. So when they repel, they give you the convex bulge or deviation. Okay. Now let's see how we do on time. You got till what, 2:30? Okay. We might get out early. For each of the following solutions, would you expect it to be relatively ideal with respect to Reynolds law? Show a positive deviation or a negative deviation? Well, which ones are most like each other? Hexane and chloroform? Yeah, I think they're pretty similar. And they have very low, almost zero delta H of a solution. So I would expect the first one to be ideal. Ethyl alcohol and water, they have a strong attraction for one another. I would think a negative deviation for a B. And then, you know what? I take that back. A should be a positive deviation. No, B should be a positive deviation. No. Let me write those on the board. I'm confusing myself. The first one is hexane and chloroform. Second one is ethanol and water. And the third one is hexane again. And octane. There we go. This one should be ideal. These are both hydrocarbons. They have London dispersion forces here, and then London dispersion when you put them together, which kind of, it's a wash. The delta H is virtually zero. So this one I think would be ideal. These two have a relatively strong attraction for one another because this one has the availability of hydrogen bonding, you know, the O and the H. So you can get hydrogen bonding there. With water hydrogen bonding, there's a strong attraction. So I would think a negative deviation, right? The concave, the negative deviation. And these, hexane and chloroform, hexane is like this one, it's non-polar. Chloroform is slightly polar. It's let's see. Trichloromethane, I think, is the proper term for it. Trichloromethane. There we go. I think that's chloroform. So the molecule itself is going to be like this, chlorine, chlorine, chlorine with a hydrogen up here. So you got your dipoles here, here, and here, right? So it's going to be a polar molecule. And this is non-polar, so they don't like each other. And then it gives you a positive deviation. Now let's see, does it have answers? No, it doesn't. You have to take my word for it. Okay, colligative properties. All right. This is what we're going to use in our next lab. One of these colligative properties. We have to define what a colligative property is. A colligative property of a solution is one where the quantitative determination, the value, depends only on the concentration of the solute, right? And not on the nature of the solute. In other words, you can put any solute in solution and it will give you the same results for the same concentration. And it doesn't matter what it is. You could say, say we were trying to reduce the freezing point of water during the winter on the roads, so we don't slide around on the ice. Right? They throw salt out, right? Sodium chloride. They use that because it's cheap and it works down to a certain temperature. But if it gets colder, you need a different salt. Yeah, calcium chloride. And they use that in mixtures or pure sometimes. And I'll show you why that works in a few minutes. But it doesn't matter that you put calcium chloride or sodium chloride out there. The freezing point depression is due only based upon how many moles of substance are dissolved in the water. And while we're on the subject, right, sodium chloride, when it goes into solution, it breaks up into one sodium and chlorine, right? When calcium chloride goes into solution, it breaks up into one calcium, but two chlorides. So for the same number of moles of calcium chloride, you get an extra third here. And that's why you can use calcium chloride to a lower temperature, because you get a higher concentration in solution. And I'll talk about it a little more in just a minute. But these are colligative properties, the ones that we're going to talk about today. Boiling point elevation. In other words, if you add a solute, it's going to cause the boiling point of the pure substance to increase. Right? So in the summer, that's good for your car's engine. We put ethylene glycol in there at a certain concentration, and it means the coolant in your engine won't boil when it gets up to 280 degrees or whatever the thermostat's set at for that engine. Or in the winter, it will also depress the freezing point. So the temperature may get down to minus 15. I've seen it that low here. You probably, if you've lived here for any time, you've probably seen it lower. But if you have enough antifreeze in your engine, the freezing point will be depressed below minus 15. And in the winter, when I buy my, I use Rain-X in my windshield washer, and they have different formulations for the summer. It's like it'll go down to 10 degrees Fahrenheit. But in the winter, they make a solution that goes down to minus 20. And you put that in there, and that guarantees that your washer fluid won't freeze and blow out your tank or your lines. Anyway, those are two colligative properties based upon the molar concentration of the solute. Osmotic pressure. Right? Osmotic pressure depends on the relative concentration of solutions across a membrane. So if we have say a sodium chloride aqueous solution on this side and water on this side, pure water, and it's what we call a semi-permeable membrane, it only lets water pass. Right? What's going to happen? Well, you've got fewer water molecules here per unit volume because you've got this in here. And the net movement is going to be that way. Right? So this solution would be we'd say that it has a high osmotic pressure, because if this is a sealed vessel and that water starts to move, the pressure is going to go up as you try to squeeze more water into that space. The vapor pressure will also vary. The vapor pressure varies with concentration. Actually, we did that one already.
So,
Oh, no, we did Henry's law. We did Rayo's law too. Yeah, we did that one already. These are called colligative properties. Simply because they only vary with the concentration of the solute. Now, the nature of the solvent does have a bearing on these values, and I'll show you how that works in just a minute. Remember when we were doing compositional analysis of compounds and trying to determine the empirical formula and the molecular formula, right? So you had percent composition, right? And you could do the empirical formula, but then you needed to know what's the molar mass before you could go the next step. How did you determine the molar mass when you don't know what the compound is? Right? Well, you use one of these methods, right? Because it doesn't matter what the compound is, it only matters how many moles. So if you know how many moles are in the solution, when you determine one of these, for us it'd be freezing point depression, then from this relationship, you can determine how many moles are in the solution. And if you weigh out your sample before you put it in solution, you have mass. Now you know moles, you can do molar mass. Okay. And you don't have to know what the compound is. So that's where those values came from in that particular chapter. So boiling point elevation. All right. So we're focused on a change in temperature. So what does that change in temperature mean? Well, this particular delta T is reference to the, actually it's an absolute value. We don't care if it's positive or negative. Well, boiling point elevation, it's going to be positive, right? The after temperature is going to be higher than the before temperature. Normally, when we say delta T, we say final temperature minus initial temperature, right? So the final temperature is for the solution, and the initial temperature is for the pure solvent. Okay, so we determine what is the boiling point for the solvent. Okay, then we put a known amount, we mass it, we put a known amount of solvent, solute in the solvent, and we measure the boiling point again. And the boiling point will increase. So we subtract those two and we get that temperature change. Okay, the temperature change that we measure is related to using a proportionality constant. They use a capital K, so let me be consistent. A capital K and the molal concentration of the solute. And remember, molality is moles of solute per kilogram of solid. Okay. And this value changes with the identity of the solvent. Okay. So you have to know that. And then you can measure this one and you can determine what this is. And if you can determine what the molal concentration is, and you already know the mass of the solvent into which you put it, and say then you can solve for the number of moles of solute that you put in there. And if you masked it before you put it in there, now you have mass in moles. You can calculate the molar mass. Okay, that's the reason we use molality, because we're looking at a temperature change here. We want the temperature to change based upon the concentration of the solute, not based upon the volume. Right? If we use molarity, then as the temperature changed, this thing would be all over the place. It wouldn't be consistent. So that's why we have to use molality instead. All right, this is the one we're going to use, freezing point depression. I'll leave that there. All we need here is a different a different constant for our solvent, and you'll be given that. And then determine what is the molality of the solute for this freezing point depression. The freezing point is going to drop when you add solute to it here. And since the freezing point is decreasing, you're going to have a low value minus a higher value from the beginning, and it's going to give you a negative value. That's why I put absolute value. We only want to know the positive difference. Okay. In this case, we don't care about the negative. All right. This is trying to explain about the vapor pressure and the freezing point. These are phase diagrams of both the pure substance, in this case water, which is the red. The red one is water. So you can see the phase line here, the phase line here between gas and liquid, and the phase line here between solid and liquid, and the phase line here, which continues on down, between the solid and the gas. And there's your triple point. That's for the pure water, if water is your solvent. When you add a solute to it, you shift the phase diagram down this direction, and it decreases this one here. So there's the difference in boiling point. Right? Boiling point is between liquid and gas, right? So that it would be between these two. And freezing point would be between these two, right? Liquid and solid. So there's the difference in the freezing point. There's the difference in the boiling point. And it's all based upon that phase diagram. All right. So a solution was prepared by dissolving 25 grams of glucose in 200 grams of water. So mass of glucose is 25 grams, 0 grams, and the mass of water, which is the solvent, is 200 grams. Oops, left out a 0. There we go. Okay, then the molar mass of glucose. Okay, so we're working back. They're going to give us the molar mass of glucose. So molar mass of glucose is 180.16 grams per mole. What's the boiling point of the solution in degrees C? And by the way, that temperature is degrees C. It can be K, it doesn't matter. They're the same size units, right? So if it's K, you subtract the two and you get the same difference. Okay, so it doesn't matter. You don't have to convert it to K though. That's the point. Glucose is a molecular solid that is present as individual molecules in solution. That's important. We're trying to find the boiling point. Right, so the temperature boiling point for this solution. And glucose does not dissociate when it goes into solution. The reason that that's important is this delta T is equal to K for boiling point, boiling point, times the molality. The molality is the moles of individual particles per kilogram of solvent. Now, if you, and I alluded to that earlier, if you get something that's not glucose, like sodium chloride, you have this many grams of sodium chloride, you might have so many moles of sodium chloride, but how many moles of particles do you have? Twice as many. So that's what goes here. Well, you have twice as many moles of particles if it dissociates. So that's why it says glucose does not dissociate. So when we have 25 grams of glucose here, we know we have so many moles. Right? 180.16. And that's how many moles of glucose we have. 25 and 180.16 divide, that's 0.1388 mole of glucose. Okay. How many kilograms of solvent do we have? Right. Unit gets bigger, that gets smaller by a factor of what? 1,000. Kilograms of water. Okay, so we can calculate the molal concentration. That's mass. Get these confused. This is molality. The molality would be moles of glucose per kilogram of solvent. Okay. And that's 0.6938. We could write the little molal there. That works. Yeah, that works. We can do that. If you're trying to get at a portion of that, like moles of your solute, then you may want to write this as moles of glucose per kilogram of water when you put it into your formula, especially if one of them is unknown. But we'll talk about that again later. All right, so our formula, we want to know what's the boiling point of the resulting solution. First of all, we can find out what the difference in temperature is. Right, delta T is equal to, they didn't give us the K. What's the K? What's the K for water? Boiling point elevation for water. Is it in there? Is it boiling point elevation for pressure? That's freezing point depression for water. Where's boiling point elevation? I'm looking at one of the subsequent slides. Ooh, that was a boo-boo. Gotta have the value. Let's look it up. All right. So let's say let's start off with water. Boiling. Elevation. Constant. There it is. Constant. Here, down the bottom. Here it is. 0.512. So K for water, boiling point equals 0.512. And what are the units? They're, well, let's look at it like this. Molality. And molality is moles per kilogram. And we want to end up with temperature. So these units are going to be degrees C per molal. Actually, we don't need that part. This way the molality will cancel and leave 3. So this is 0, this is degrees per molal. Okay. Let's see how I got that. Or did I blow everybody? I was just using the formula to tell me what the units were here. They have to be degrees per molal because molal has to cancel and leave us with degrees C. That's all I was doing. Okay, so that's our value. So that means the change in temperature is going to be equal to 0.512 degrees C per molal times what's the molality? 0.6938 molal. So the change in temperature give me my calculator. There it is. It is. I've already got that one in here. Just put this one in. Times. Okay, so this is 0.355, say, degrees C. That's the change in temperature. That's the boiling point elevation. So what's the boiling point of water? Pure water is 100 degrees, right? So the boiling point elevation would be 100.355. Or rounded off. Let's see. Let's see what the authors did. .35. There you go. I need to make a note. 0.512 on this slide so I can change it. I don't want to have to keep looking it up. K boiling point for water equals 0.512 degrees C per molal. Make it up later. Okay. This is the Van Hoff factor. And the Van Hoff factor is a way of modifying the colligative property formula to account for dissociations. When you put the compound in solution, does it remain whole? In which case the Van Hoff factor would be 1. It would look something like this. Like that. And that I would be equal to 1 or no dissociation. Okay. Generally speaking, if your compound is an acid or a base or a salt that dissociates when it goes into solution, the number of parts or ions that it produces would be your Van Hoff factor. So I would be 2 for, say, sodium chloride. I would be 3 for calcium chloride because it would break up into 3 parts. Or I would be 4 for, let's see, think sodium phosphate. Do that. Sodium phosphate. Right, 3 plus 1 is 4. And that would go in here. Now, as a practical matter, the Van Hoff factor is usually not, actually, it's not fixed. Right? It varies with concentration. So if it's a dilute solution of these, then yes, it would be very close to a simple adding up of the number of ions. But if they're very concentrated, I think that's on the next slide, you get ion pairing. If the concentration is very high, then you get some of those ions that go back and recombine in solution. And that reduces your Van Hoff factor. So if sodium chloride were at very high concentration, your factor might be 1.9 or 1.8. Right? And I'm not going to saddle you with anything like that. I just want you to be aware of that fact. That theoretically it's whole numbers, but if the concentration gets high, and this value will change as the concentration changes. Right? And if I were an engineer, I just have a book of tables. Let's see, what's the concentration? Look for the Van Hoff factor, plug it in the formula. Okay. Oh, it's also important for very highly charged ions. So it would be more important for something like phosphate that has a 3- charge. Or if we had calcium phosphate. Let's not do that. Let's say calcium phosphate is insoluble, so I can't use that one. Magnesium phosphate. I can't think of a good example. But the higher the charge, the more pronounced the ion pairing is. Okay. So there's your modified equation using the Van Hoff. This one might take us a little time. Did I work it out in the slides? Yes. Yeah. Good. Okay. So I don't have to depend on my memory to work this one. So in this particular problem, we've got 20 grams of sucrose and sodium chloride mixture. So we actually have mass equals 20 grams of both. Sucrose plus sodium chloride. Okay. And in 1 liter of water. So the volume of the solution of the solvent is 1 liter or 1 kilogram. The freezing point of the solution is minus 0.8426. So if the freezing point of this solution is minus 0.426 or 6 degrees, what is the delta T? Right? It would be 0.426 C. Oh, no, yes, it would, because the freezing point is 0. So it's that much below 0.426. So we know what our delta T is. Assume ideal behavior, calculate the mass percent composition of original mixture in the mole fraction of sucrose. Okay. So we've identified all the salient bits of information. Come on, there we go. So if we let the mass of sucrose equal X, then the mass of sodium chloride, the mass of sucrose equals X, and the mass of sodium chloride equals 20 minus X. Okay. And then we define the number of moles of sucrose based upon the molar mass formula, 342.34 grams per mole. And that just says the molecular weight is mass per moles. And we want to solve for moles, so we put this over here and put mass over molecular weight. So that's where that N of sucrose, the mass of the sucrose, comes from. That's the unknown mass here divided by the molecular weight. And we do the same thing for sodium chloride, right? Only sodium chloride is 20 minus X divided by its molar mass, 58.45. So the molality of the solution then is the combination of those two moles, those formulas, these two formulas right here, that one and that one. That's the total number of moles divided by the mass of the solution. That's the molality of the solution. Okay, that's how far we've gotten so far. The Van Hoff correction factor for sucrose is 1, and that for sodium chloride is 2. So keep that in mind. The K value for freezing point depression is 1.86 degrees C per mole out. And the change in temperature, we've got that already right here, 0.426. Okay. And go to the next slide. Now what we're doing is setting it up with the formula. This is equal to whatever the I is, and the K value, and the molality, the total molality. Well, this, if we solve this equation, right, if we put these values in here, where we have I times the molality, and then we have this value of 1.86, right? That's the constant degrees C per mole out. And we bring that over here, and the degrees C cancel and leaves us with molality. Okay, and that turns out to be 0.2290. So this I times M, and we don't know what I is yet. We have to talk about that in a second. Is equal to 90. And this is mole out. Okay, that's how far we've gotten. Now, the total value over here is the summation of the two. So we got a value for this one for sucrose and this one for sodium chloride, and we have the individual I's here. So these two sum, that's the trick right there, right? You may not know that that's valid, where you can add these two values together. And if that's the case, then it's simply solving for X now, and which will go all the way down through and go to the next slide and solve for X. That means we have 14.55 grams of sucrose and 5.45 grams of sodium chloride. Now to calculate the mass percent, that's a simple procedure. But we want to know mole fraction too. So the mole fraction of sucrose is simply the moles of sucrose divided by the total moles, and that's 0.3131. And if we wanted to know the mole fraction of sodium chloride, we just subtract that from 1. No, we wouldn't. Why? Yes, we would. Right. Mole fraction in the undissolved compound. Right? Okay. But that answers the question that was asked. All right. This particular, you know what? I think these slides are out of order. A plant cell has a natural concentration of 0.25 mole. If you immerse it in aqueous solution with a freezing point of minus 0.246, will the cell explode, shrivel, or do something, or do nothing? Oh, okay. Yeah, we can answer this. This refers to osmotic pressure, right? And if you had, has everybody had anatomy and physiology? Right. So you know about isotonic, hypotonic, and hypertonic. Okay. So if the solutions are isotonic, nothing will happen. If the solutions are hypertonic, then the water is going to move from the lower concentration of solute to the higher concentration of solute to the hypertonic solution, and the cell will shrivel, and the other way around, it'll explode. Okay, so all we need to do, since we know the cell concentration is 0.25 mole out, we just need to calculate what is the molality of the solution that surrounds it. And that's what we do here. Okay. So the difference in temperature is the question. We don't know what the difference. We know what the freezing point is, right, for the solution. So that T of solution, we do know that, and that's substituted right down. Let's see, right down here, there, and the T of the solvent, of course, is water, so it's 0. And the difference, whatever the difference is, it's going to be absolute value anyway, right? It just turns out to be a positive value because we did it right. But the molality here is the unknown. So we solve the molality for 0.132 outside the solution. So what's going to happen? Outside the solution is hypotonic. So it's got more water outside the cell than inside the cell. The cell is 0.25. So water is going to move into the cell and eventually it'll explode. Let's see. There we go. Water will move into the cell and that's all she wrote. It will pop. I saw this, I think it was on YouTube. There was a video of a teacher who wanted to show his class red blood cells under the microscope. So he pricked his finger and smeared some on the scope or put a drop on the slide. And it was too thick, right? The light wouldn't shine through it well and you couldn't see the cells. So he put this little drop and he put some water on it to, spread them out. Well, he made the mistake of putting distilled water. So in the time it took him to take the slide and put it under his scope and focus it, it was nothing but a pink solution. The water had gone into the cell and boom, lysed every one of them. Okay, osmotic pressure, that's what we're getting at. Osmosis is the flow of the solvent into the solution through a semi-permeable membrane. Now, actually, when we say flow of solvent, when we're saying semi-permeable, semi-permeable membrane, what we're saying is that only water and gases will pass through the membrane. Nothing else goes. There's another type of membrane that's often used. It's called, it has two names actually. It could be selectively permeable or differentially permeable. And in these, passage depends upon usually molecular size, but it can also depend on other things like electrostatic charges and that. But typically, when I do the lab, this one, I don't think I do this the lab here with that one. I think I do that with Logan. But if you use a selectively permeable membrane, then it will let things through based upon their molar mass. When we talk about semi-permeable membranes, the implication is that only water and gases will flow through the membrane. Osmosis is the process of movement of water. We're going to stick with water moving through that membrane in response to a difference in concentration on either side of the membrane. And you can build up a pressure as a consequence. Now, when we write out the formula, pi, that's what this is, pi, equals molarity times the gas constant times temperature. So in this case, we can use molarity because we're taking temperature into account in the process, in the calculation. We don't have to use molality. Molarity works. And this is going to be in Kelvin, right? Because that one is in Kelvin. And this value, if we want this value to come out as atmospheres, which one of these R's are we going to use? Liter, atmosphere, or mole. Okay. We use the first one we learned with gases. That way, K cancels. Moles per liter is the inverse of molarity. So this one cancels with these two right here and leaves us with atmospheres. Okay. And that's how we calculate the osmotic pressure of a solution. Right? Here's what that pressure means. If we have the solvent surrounding this bulb, and the membrane is attached to the bottom of that bulb, and the solution is inside the bulb, then the water we know is going to move into the bulb. Right? If it's pure solvent outside, then it has to move in. And what it's trying to do is to balance the rate of movement of water molecules across that membrane. And if you've got a pure solvent on this side of the membrane, pure water here, and you've got a solution up here, then the concentration of water is less up here than it is down here. So the rate of flow of water is going to be that, like that, and it's going to be like that, going the other direction. So it's going to move into the solution, trying to establish an equilibrium based upon the rate of movement. Okay? And the rate of movement is dependent upon not just the concentration, but the push behind it, a pressure. So as we increase, as water moves into this, you'll see the rise here, and that's applying an added pressure against that membrane as it rises. And when it reaches the point where that pressure balances the pressure from the outside, from the water moving in, those two pressures are equal, then the rates of movement are also equal, and it stops. And that difference between where it was and where it is now, relative to the solution, because the solution is going to drop. See, the solution there is here, and it drops down here because it's been moving in. So we have to measure the pressure from here to there. That difference in height, in whatever unit you choose, is a measure of the osmotic pressure of that solution. This is another way to express it. But it's still the difference in the heights of the solution. Once they stop moving, then the osmotic pressure is the difference in those heights. And you can express that as a difference in height of water column, right? And there's a relationship between that and mercury, right? It's based upon the density. Right? I think, what's the difference? Mercury is 13.5, I think, grams per cubic centimeter, where water is 1. So it's 13.5 times that would be the water level. So you divide 13.5 into the water difference in pressure, and you get your mercury difference in pressure. Okay, so Van Hoff can also be applied here. Right? If you put sodium chloride in solution at 1 molar, you're actually going to get 2 molar, or maybe a little less, because that's pretty high concentration. But you're going to get twice the value. I would be equal to 2. So you use the same type of correction factor here, because it's dependent upon the number of particles. It doesn't depend on what went in. It just depends on what is in solution after it goes in. All right. 1:30. Ooh, I'm out of time, right? Did I read that right? Yeah, I'm out of time. How many more slides do I have? I may have to skip 1 or 2. Yeah, okay, so I'm gonna move pretty quick on the last slides. So 33.4 milligrams of a compound is dissolved in 10 milliliters of water. Right, we don't know. We know the mass of the compound, but we don't know the moles of the compound. The solution has an osmotic pressure of 558.4. Calculate the molar mass of the solution. Let's see. Oh, there it is. Okay. So we know that the osmotic pressure is going to be so many atmospheres because of the constant that we're using is right here. And the units of measure there are liter atmospheres per mole K. We have to convert the pressure to this many atmospheres. And the K temperature is here. This gives us the molarity of the solution. And then we use the relationship of molarity equals moles per unit volume. Right? We want to know the number of moles because we know the mass. Now we need the moles and we can calculate the molar mass. So N equals molarity times volume. And that's the number of moles. We calculate the number of moles and then do the calculation for molar mass. And there you have it, 106 grams per mole. This is an interesting problem. I'll just outline it and leave it there. I often wondered, with a tree that's 350 feet tall, how does the water or the sap get from the roots to the top? Because if you have a tube and you stick it in a pan of water at 1 atmosphere pressure and you pull a vacuum on the top, just like you were making a barometer with water, how high would the water rise? The water only goes up 33 feet, right? Talk to a scuba diver. For every 33 feet you go down in the water, you get an extra atmosphere of pressure on your body. Well, 33 feet is not going to make it to the top. At one time, I thought the theory was, well, maybe it's not pressure, it's not a push, it's a pull. You know, the water goes, it starts as a little tree, so it's already got the column of water moving, and it's got spiracles up here in the leaves, and the evaporation of water, right? Right, it goes like that, and the surface tension pulls it up like that, and it's enough to pull the water up to the top. That's been disproved by experiment. So it is a push, but I was approaching it from the wrong direction. If you measure the osmotic pressure of the sap in the tree roots, you find that the pi, the osmotic pressure, is 20 atmospheres. It's extremely high. Is that enough to reach the top of the tree? So that's the calculation we're doing here. Say it's only 300 feet. Okay, 300 feet would be that many millimeters tall. Right? So how many millimeters? That would be millimeters of water, for instance. So how many millimeters of mercury would that be? Well, there's a millimeters column of water. Right? If it's 20 atmospheres, then it should be able to support 2 times 10 to the 5th millimeters of water, and we only need 10 to the 4th. So yeah, you'll make it to the top. So it is a push after all. And that, you know, when you think about it, that makes more sense. Because what if you go through a drought, right? And the tree shuts down? It doesn't have that continuous column of water anymore. Right? So you can't pull if there's nothing to pull on. So, colloids. What is a colloid? A colloid is not a solution, it's a suspension, but it will stay a suspension indefinitely. And it's based upon the size of the suspended particles. If the suspended particles are small enough, then the kinetic energy of the suspending medium is sufficient to bang against them and keep them in suspension. Right? So a colloid is kind of between a suspension and a solution based upon particle size. And let's see, we're going to do, it's exercise 5. the formation constant of a complex ion. So we're going to titrate silver with chloride ions, and we have to detect where that endpoint is. Where do you start to form that silver chloride in suspension? And we use the Tyndall effect. We just dim the lights and have a flashlight shining through, and you can see it. And you see the beam going through there. It's pretty cool. That's the Tyndall effect, and it's based upon the concept of colloids. The size of the ions of the molecules between 1 and 1,000 nanometers, those will stay in suspension. Jello is a good example. There's some others. I'm going to let you look at those at your leisure. These are, be sure and look at them though, because there might be questions. What are the names of these different types of colloids? We show you one of them. Okay, the foam, that's a gas in a liquid, is a colloid. What is coagulation? Well, when you have a colloid, say you have, especially proteins, if you have proteins in solution, and you can heat them up, or you can salt them out. You just change the salt concentration and they'll drop out of solution because they stick to one another.